Hello there, and welcome to Science for Sleep, a place where curiosity is invited to slow down, settle in, and wander gently without needing to arrive anywhere in a hurry. This is a space where science doesn't rush to impress, where questions are allowed to breathe, and where even the most complex ideas are explored at a pace that feels unhurried and kind. Tonight, we're going to spend some quiet time with something incredibly small, something you've encountered every day of your life, something that has touched your skin, your eyes, your thoughts, without ever announcing itself. We're going to talk about light, and more specifically, we're going to ask a deceptively simple question. What is a photon actually made of? That question sounds straightforward at first. It feels like the kind of thing that should have a tidy answer, maybe something you could point to, name, or imagine as a tiny object flying through space, and yet, the moment you pause with it, really pause, it begins to soften and stretch. Because photons are strange guests in our understanding of the universe. They are everywhere, yet impossible to hold. They're essential, yet oddly elusive. They warm your face in the morning, carry images into your eyes, and allow information to travel across unimaginable distances. And still, when we try to ask what they're made of, the answer resists being boxed in. Before we wander too far into that mystery, take a moment to notice where you are right now. Are you listening from a quiet room, a softly lit space, maybe under a blanket or with the day finally behind you? Is it late where you are, or early, or somewhere in between where time feels a little less strict? What part of the world are you in as these words find you? Light behaves differently depending on where it is, after all, bending, scattering, arriving at different angles depending on where you stand, and you, listening right now, are part of that landscape. If you find this kind of gentle exploration calming, or if you enjoy letting scientific ideas drift past as you rest, then liking the video or subscribing is a small way to help this quiet corner reach others who might need something similar. There's no urgency in that, just an open invitation, like leaving a porch light on rather than ringing a bell. And now, with nothing you need to do and nowhere you need to go, we can begin easing into the story itself. When most of us think about light, we think about what it does, not what it is. We think about brightness and darkness, about colours, about whether a room feels warm or cold. We flip switches, we open curtains. Light arrives, and we accept it without much resistance. For centuries, humans understood light mainly through its behaviour. It travels fast. It moves in straight lines. It reflects off mirrors and bends through glass. These observations were enough to build early optics, to create lenses, telescopes, and eventually the instruments that allowed us to look outward toward distant stars and inward toward microscopic worlds. For a long time, light was comfortably described as a wave. This made sense. Waves spread out. Waves interfere with one another. Waves bend around obstacles. Light does all of these things. When light passes through a narrow slit and creates a pattern of bright and dark bands on a screen, it behaves exactly the way waves on water do when they pass through an opening. This wave picture worked so well that for a while, it seemed unnecessary to ask deeper questions. Light was a vibration, something rippling through space, and that was enough. But even then, a quiet problem lingered. Waves usually need something to wave in. Water waves need water. Sound waves need air or some other material. So physicists imagine that light must also need a medium, an invisible substance filling all of space, something they called the ether. This ether was supposed to be perfectly transparent, perfectly still, and everywhere at once. It was a convenient idea, but an uneasy one. No one could detect it. No experiment could find evidence of it. And slowly, reluctantly, scientists had to let it go. As experiments became more precise, light began to misbehave. It started doing things that waves alone couldn't explain. One of the most important moments came when scientists studied what happens when light hits metal. Under certain conditions, shining light on a metal surface causes electrons to be ejected. But the details were odd. Brighter light didn't necessarily knock electrons loose. Instead, the colour of the light mattered. Below a certain frequency, no amount of brightness worked at all. Above it, electrons flew free immediately. This behaviour didn't match the wave model. If light were just a wave, then increasing its intensity should eventually shake electrons loose, regardless of colour. But nature refused to cooperate. The explanation that finally worked was radical at the time. Light, it turned out, arrives in discrete packets, little bundles of energy. These packets were later named photons. At this point, the question we're asking tonight begins to sharpen. If a photon is a packet, what exactly is inside it? Is it made of smaller pieces? Does it have structure? Does it have edges? Does it contain something? Or is it something in and of itself? The first surprising thing about photons is that they don't behave like ordinary objects at all. They have no rest mass. That means you can't imagine them sitting still, waiting to be examined. A photon is never at rest. It always moves at the speed of light. Not because it's trying to, not because it's accelerating, but because that is simply what it is. Asking what a photon looks like when it's stopped is like asking what a ripple looks like without water. This alone makes the idea of composition tricky. Most things we talk about as being made of something are assemblies. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. There's a nesting structure, a hierarchy of parts. Photons don't fit neatly into that pattern. They are not built from smaller particles in the same way. As far as we can tell, a photon is fundamental. There is nothing inside it waiting to be taken apart. That doesn't mean it's simple, though. A photon carries energy, and that energy depends on its frequency. Higher frequency photons carry more energy. This is why ultraviolet light can damage cells, while radio waves pass harmlessly through your body. But energy is not a substance in the usual sense. It's a property, a measure of capacity for change. Saying a photon is made of energy is a bit like saying a song is made of volume. It tells you something important, but not the whole story. Photons also carry momentum, even though they have no mass. This seems contradictory until you remember that momentum depends on motion as well as mass. Light can push, it can exert pressure. This is not a metaphor. Solar sails, thin reflective sheets designed to capture the momentum of sunlight, can actually be propelled through space without fuel. Each photon contributes a tiny nudge, and over time those nudges add up. So now we have a strange inventory. A photon has energy. A photon has momentum. A photon has a frequency and a wavelength. It can be polarized, meaning it has an orientation related to the direction of its electric and magnetic fields. And yet, it has no mass, no size in the usual sense, and no internal parts we can point to. This is where modern physics offers a different kind of answer. Instead of asking what a photon is made of, it asks what a photon is an expression of. In quantum field theory, which is our best framework for describing particles and forces, the universe is filled with fields. These fields are not objects. They're more like underlying rules that exist everywhere. Each type of particle corresponds to a field. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons, in this picture, are excitations of the electromagnetic field. That field exists everywhere, even in empty space. When it vibrates in a particular way, when it carries energy from one place to another, we perceive that excitation as a photon. The photon is not a little bead flying through space. It is a localized ripple in a field that fills the universe. This doesn't mean the photon is made of the field the way a statue is made of marble. The field is not material in that sense. It doesn't have atoms or texture. Or it is more accurate to say that the photon is the field doing something specific. A temporary quantized event. A transfer of energy that cannot be divided below a certain limit. If that feels unsatisfying, you're not alone. Even physicists often struggle with the language here. Our intuition evolved in a world of solid objects and continuous substances. Quantum fields don't behave like either. They're abstract, but their effects are concrete. You can feel sunlight. You can see a candle flame. You can measure the energy of individual photons with astonishing precision. Whatever a photon is made of, it is real enough to warm your skin and register on a detector. Another important aspect of photons is that they do not experience time. This is not a poetic statement. According to relativity, time slows down as an object moves faster. At the speed of light, time effectively stops. From the photon's perspective, if such a perspective can be meaningfully defined, there is no passage of time between emission and absorption. A photon emitted by a star billions of years ago does not age. It does not experience a long journey. It simply exists at the moment of interaction. This has an interesting consequence for our question. Composition usually implies persistence through time. A thing is made of parts that exist together over a duration. But a photon, in a very real sense, does not endure. It is created and absorbed, and in between it does not experience becoming. It is an event rather than an object, a process rather than a container. That idea begins to blur the boundaries of what we usually mean by made of. Perhaps photons are not made of anything in the traditional sense. Perhaps they are the smallest possible units of interaction, the minimal acts by which the electromagnetic field communicates change. And yet there is still more to say because photons interact. They are emitted by atoms when electrons change energy levels. They are absorbed by atoms, transferring that energy back into matter. They can scatter, reflect, refract. They can be entangled, linked in ways that challenge classical ideas about separation. These behaviors suggest rules, structure, constraints. Not internal components, but defined characteristics that shape how photons exist. For now, it's enough to sit with the idea that a photon is not a tiny thing packed with smaller things, but a precise, indivisible expression of something deeper. Light is not built the way furniture is built. It is closer to a rule being briefly enacted, a message passing through the universe in its simplest possible form. Light does not announce itself when it arrives. It doesn't knock, doesn't pause, doesn't ask whether you're ready. One moment a place is dark, the next it isn't, and the transition feels so ordinary that we rarely stop to consider what just happened. Something crossed the space between a source and your eyes, carrying information with extraordinary precision. Not heat alone, not colour alone, but a detailed report about the world as it is right now. That something is what we call a photon, and in many ways it is the smallest and most reliable messenger the universe has ever produced. When scientists describe photons as messengers, they are not being poetic. Photons are how the universe communicates with itself. Every time a star forms, every time an atom rearranges its electrons, every time a chemical bond vibrates, photons are created or absorbed. They move energy from place to place. They carry signals. They tell distant regions of space that something has happened somewhere else. Without photons, the universe would be silent, blind, and thermally frozen into isolated pockets with no awareness of one another. What makes this messenger so remarkable is not just what it carries, but how little it needs in order to do its job. A photon has no rest mass. It has no internal machinery ticking away. It doesn't wear down with use or lose pieces along the way. It doesn't require fuel. Once created, it moves at the same fixed speed, regardless of where it came from or what it passes through, until it is absorbed. That consistency is not a convenience. It is fundamental. It is why the universe can rely on photons to deliver information faithfully across distances that stretch beyond imagination. Consider what happens when light leaves the surface of the sun. In the sun's core, nuclear reactions release energy that takes thousands of years to work its way outward through dense plasma. But once that energy finally escapes as light from the surface, the journey to Earth takes about 8 minutes. During that time, individual photons cross nearly empty space, unimpeded, maintaining the exact properties that encode their origin. The warmth you feel on your skin, the brightness you see when you look at the sky, is ancient energy delivered with extraordinary efficiency. This messenger role becomes even more striking when you think about vision. Your eyes do not reach out and touch objects. Instead, photons reflected or emitted by those objects enter your eyes and interact with specialized cells in your retina. Each photon triggers a tiny chemical change. Billions of these changes are processed by your brain, constructing a picture of the world. You are not seeing objects directly. You're interpreting messages carried by photons, messages that have bounced, scattered, and travelled, all without losing their essential content. Yet despite how central photons are to communication in the universe, they are surprisingly minimal in what they bring with them. A photon does not carry a label saying where it came from. It does not remember its past. It does not know its destination. All it has are its intrinsic properties: energy, momentum, polarization, and direction. From these few ingredients, everything else is inferred. This simplicity is not a limitation. It is a feature. Because photons are so minimal, they interact with matter in predictable ways. When a photon encounters an atom, the rules governing that interaction are precise. The photon may be absorbed if its energy matches an allowed transition. It may scatter, changing direction. It may pass straight through. There is no ambiguity in the rules themselves, even if the outcomes are probabilistic. Calling the photon the smallest messenger is not just about size, it is about granularity. Photons are the smallest possible units of electromagnetic interaction. Light does not arrive as a continuous drizzle at the most fundamental level. It arrives in individual quanta. Even the faintest glow is made of countless discrete events, each photon delivering a specific packet of energy. This granularity matters because it sets limits. It defines the smallest possible signal. You cannot send half a photon. You cannot divide one into smaller electromagnetic messengers. This discreteness is what makes technologies like digital imaging, lasers, and quantum communication possible. It is also what introduces noise at very low light levels. When light is scarce, the randomness of individual photons becomes noticeable. Darkness is not the absence of light entirely, but the absence of enough photons to reliably build a picture. Despite being indivisible, photons are not identical in the way grains of sand might be. They can differ in energy, which corresponds to frequency and colour. A radio photon and a gamma-ray photon are both photons, but they exist at opposite ends of the electromagnetic spectrum. One carries so little energy that trillions pass through your body every second without effect. The other carries enough energy to damage DNA. Same kind of messenger, very different messages. This spectrum reveals something important about what photons are not. They are not particles in the classical sense with fixed size or shape. A photon's wavelength can be longer than a football field or shorter than the diameter of an atom. Asking how big a photon is misses the point. Its spatial extent depends on how it is created and how it is measured. Sometimes it behaves like a localized packet. Sometimes it behaves like a spread-out wave. These are not contradictions. They are reflections of how photons interact with measuring devices. As messengers, photons are also impartial. They do not prefer one direction over another. They do not slow down with age. They do not weaken unless they interact. In empty space, a photon can travel for billions of years without change. When we detect light from distant galaxies, we're receiving messages sent long before Earth existed. The universe has been speaking for a very long time, and photons have been carrying the conversation. One of the most subtle roles photons play is in maintaining cause and effect. Because photons travel at a fixed maximum speed, they set the ultimate speed limit for information. Nothing that carries information can travel faster. This ensures that causes precede effects in all reference frames. Without this limit, the universe would become deeply unstable at a logical level. Events could influence other events before they happened. The photon's speed is not just a number, it is a structural feature of reality. In this sense, photons are not just messengers within the universe. They help define how the universe is allowed to work. They enforce consistency. They connect distant regions while preserving order. Every signal, every observation, every measurement relies on photons obeying these rules. It's also worth noticing that photons do not travel alone conceptually. They are deeply tied to electric charge. Wherever there is a change in electric or magnetic fields, photons can be involved. They mediate the electromagnetic force, which means they are responsible for interactions between charged particles. When two electrons repel each other, that interaction can be described as an exchange of photons. These photons may be virtual, not directly observable, but they play the same messenger role, carrying influence rather than visible light. This expands the idea of messaging beyond images and warmth. Photons carry force. They transmit influence. They allow particles to affect one another without touching. This is not metaphorical distance. It is real separation bridged by photon exchange. Matter does not reach across space. Photons do the reaching. Despite all this responsibility, photons remain strangely anonymous. Unlike electrons or quarks, they do not carry charge. They do not participate in the strong or weak nuclear forces. They do not clump together to form structures. They do not make up matter. They pass through matter, interact briefly, and move on. They are involved everywhere, yet belong nowhere. This makes them ideal messengers. A messenger who becomes part of the message risks distortion. A messenger who interacts too strongly might alter what it carries. Photons strike a balance. They interact just enough to deliver information, but not so much that they lose their identity in the process. There is also an elegance to how photons are created. When an electron in an atom drops from a higher energy level to a lower one, the energy difference is released as a photon. That photon's energy precisely matches the difference between the two levels. No more, no less. This precision is why atoms produce characteristic spectra, and why we can identify the composition of distant stars by analysing their light. Photons act as stamped envelopes, each one marked with information about the process that created it. At the same time, photons can be destroyed just as cleanly. When absorbed, they do not leave fragments behind. Their energy and momentum are transferred to whatever absorbs them. The photon ceases to exist as a separate entity. There is no debris. This birth and absorption pattern reinforces the idea that photons are events rather than objects. They are interactions that propagate. Thinking of photons this way helps explain why asking what they are made of often leads to confusion. A messenger made of parts could break down, degrade, or change en route. Photons do none of these things. They are defined by their role, not by internal composition. They are the smallest units by which the electromagnetic field can say, something happened. As technology advances, we are learning to use photons not just as passive carriers, but as controlled signals. Lasers produce photons that are highly organized, all moving together with the same frequency and phase. Fiber optic cables guide photons across continents, encoding vast amounts of data. Quantum experiments entangle photons, linking their properties in ways that defy classical intuition. In every case, we are exploiting the photon's reliability as a messenger, yet for all this utility, photons retain an air of strangeness. They cannot be stored easily. They resist localization. They do not behave like little bullets or beads. They are more like rules in motion, constraints expressed dynamically. When we say a photon travels, we're using language that only approximates what is happening. Still, the approximation is good enough to build an entire technological civilization on. That should tell us something important. Whatever a photon is made of, it does not need solidity to be effective. It does not need structure in the traditional sense. Its power comes from consistency, from being the same kind of thing everywhere and every when. Long before anyone spoke about photons, quanta, or packets of energy, light already had a respectable career as something far more familiar. It was a wave, not metaphorically, not approximately, but confidently and convincingly so, at least according to the best minds and experiments available at the time. For centuries, the wave description of a light didn't just work reasonably well, it worked beautifully. It explained reflection, refraction, diffraction, and interference with an elegance that felt deeply satisfying. And for a long while, there was little reason to think light needed to be anything else. To understand how complete this picture once seemed, it helps to step back into a period when physics was still assembling its basic vocabulary. Motion had rules, forces had causes, matter was made of tangible stuff. Waves, meanwhile, were a known quantity. People had watched ripples spread across ponds, heard sound travel through air, and felt vibrations pass through ropes and strings. Waves were disturbances that moved through something. They carried energy without transporting matter from one place to another. That idea alone made them attractive candidates for explaining light. Light travelled from the sun to Earth, yet the sun did not shrink. A candle illuminated a room, yet nothing visibly flowed from the flame to the walls. This matched wave behaviour perfectly. A wave could move energy across space without requiring tiny projectiles to fly outward like microscopic arrows. And once experiments began to probe light more carefully, the wave model started collecting victories. One of the most important pieces of evidence came from interference. When two beams of light overlap, they can reinforce each other, producing bright regions, or cancel each other out, producing darkness. This is exactly what waves do. Water waves overlap and create complex patterns. Sound waves interfere, producing beats. Light did the same thing. Thomas Young's famous double-slit experiment in the early 1800s showed this clearly. Light passing through two narrow slits created a pattern of alternating bright and dark bands on a screen. This was not something particles should do. It was unmistakably wave-like behaviour. Diffraction added to the confidence. Light spreads out when it passes through narrow openings or around edges. Instead of casting sharp shadows, it produces soft boundaries and fringes. Again, this matched wave behaviour precisely. A wave encountering an obstacle bends around it. A stream of particles, in contrast, would be expected to cast crisp shadows unless something else was going on. Refraction fit as well. When light enters a different medium, like glass or water, it changes direction. Waves do this when their speed changes. Sound waves bend when moving through air layers of different temperatures. Water waves change direction when moving from deep to shallow regions. Light slowing down in glass and bending at the boundary felt entirely natural in this framework. By the mid-19th century, the wave theory of light was not just plausible, it was dominant. James Clerk Maxwell then delivered what felt like the final confirmation. He unified electricity and magnetism into a single theory and showed that oscillating electric and magnetic fields could propagate through space as waves. When he calculated their speed, it matched the known speed of light. This was a remarkable moment. Light wasn't just a wave, it was an electromagnetic wave. At that point, the story seemed almost complete. Light consisted of oscillating electric and magnetic fields, moving through space at a fixed speed. Different frequencies corresponded to different colours. Everything fit into a clean mathematical structure. Physics textbooks could have stopped there, and for many practical purposes they nearly did. But there was one uncomfortable detail hiding beneath the success. Waves need a medium. Water waves need water. Sound waves need air or some other material. If light was a wave, what was waving? The answer proposed was the luminiferous ether, often simply called the ether. This was imagined as a substance that filled all of space, permeating everything, invisible, massless, and perfectly elastic. It had to be rigid enough to support incredibly fast waves, yet subtle enough not to interfere with the motion of planets or objects. It was an odd substance, but physicists were willing to tolerate it because the wave theory worked so well. For decades, the ether sat quietly in equations and assumptions. It was rarely questioned directly. But as experimental techniques improved, scientists began trying to detect Earth's motion through this ether. If the ether existed, and if Earth moved through it, then the speed of light should vary slightly depending on direction, much like the apparent speed of wind changes depending on how you move through air. The most famous attempt to measure this effect was the Michelson-Morley experiment in 1887. Using an interferometer of exquisite precision, they compared the speed of light in perpendicular directions. The expectation was clear. A difference should appear. It didn't. No matter how the apparatus was oriented, the speed of light remained the same. This result was deeply unsettling. It didn't immediately destroy the wave theory, but it shook the foundation it rested on. Some physicists tried to rescue the ether by proposing that objects contract as they move through it, conveniently cancelling out the expected effects. These ideas worked mathematically, but felt increasingly strained. The ether was becoming a solution in search of a problem. Still, even as doubts about the ether grew, the wave picture itself remained powerful. It explained polarization, a property of light that only makes sense for waves. Polarization describes the orientation of light's oscillations. Filters can block light of certain polarizations while letting others through. This behavior is difficult to reconcile with simple particle models and fit naturally into the electromagnetic wave framework. By the late 1800s, many physicists felt that the nature of light was essentially settled. It was a wave. The remaining work involved refining measurements, extending applications, and exploring new phenomena within that framework. Few suspected that the calm surface hid a deeper instability. The cracks began to show in situations involving energy exchange. One of the first warning signs was black body radiation. When objects are heated, they emit light. Classical wave theory predicted that a hot object should emit more and more energy at higher frequencies, leading to what was later called the ultraviolet catastrophe. According to the equations, the emitted energy should diverge to infinity. In reality, it didn't. Experimental measurements showed a clear cutoff. At first, this seemed like a technical problem, something that could be fixed with better mathematics. Instead, it required a conceptual leap. Max Planck proposed that energy exchange between matter and electromagnetic radiation occurred in discrete amounts. This idea was initially treated as a mathematical trick. Planck himself did not believe energy was fundamentally quantized. He was trying to save the wave theory, not overthrow it. Then came the photoelectric effect. Light shining on metal surfaces caused electrons to be ejected, but only if the light's frequency was high enough. Increasing intensity didn't help if the frequency was too low. This result was stubborn. It refused to bend to wave explanations. Albert Einstein took Planck's idea seriously and proposed that light itself came in discrete packets of energy. These packets later became known as photons. At that moment, the wave-only picture began to unravel. Light clearly behaved like a wave in many experiments. It also behaved like something discrete in others. This dual behavior was not a matter of incomplete measurement, it was built into nature itself. But before moving forward into photons and quanta, it's worth lingering a bit longer in the wave-only world, because understanding how complete and convincing it once was helps explain why the photon was such a shock. The wave model wasn't naive, it wasn't simplistic, it was mathematically rich and experimentally grounded. Even today, much of our practical understanding of light relies on wave descriptions. Optics, lens design, diffraction patterns, antenna theory, and radio transmission all use wave models successfully. When engineers design fiber optic cables, they calculate modes, interference, and dispersion using wave equations. In these contexts, photons rarely appear explicitly. This tells us something important. The wave description of light is not wrong, it is incomplete. It captures how light propagates, interferes, and spreads. What it struggles with is how light interacts at the smallest scales, particularly when energy is exchanged between light and matter. In the wave-only view, light's energy is spread out continuously across space. A dim beam is just a weaker wave. A bright beam is a stronger one, but experiments show that matter doesn't respond to that smoothness. Atoms and electrons behave as if light arrives in chunks, delivering energy all at once or not at all. This mismatch forced physicists to accept a difficult idea. Light is not either a wave or a particle. It exhibits properties of both, depending on how it is measured and what aspect of its behavior is being probed. This is not because light changes its mind, but because our classical categories are too rigid. Still, at the time when light was only a wave, none of this was obvious. The success of the wave theory shaped generations of thinking. It influenced how scientists conceptualized fields, space, and energy. It laid the groundwork for later theories, including relativity, which preserved the wave nature of light while discarding the ether. In fact, Einstein's special relativity did something subtle. It removed the need for a medium while keeping electromagnetic waves intact. Space itself could support fields. The speed of light became a universal constant, not a property of a medium. This resolved the ether problem without abandoning waves. What relativity did not resolve was the quantum problem. That required a deeper shift, one that would eventually redefine what we mean by made of. Light, once thought to be a continuous ripple in an invisible substance, would become something stranger. Not a thing with parts, not a bead flying through space, but an excitation, an event, a quantized interaction. Understanding the era when light was only a wave helps anchor this transition. It reminds us that scientific models are tools, not truths carved into reality. They work within certain domains and fail in others. The wave model of light was not replaced because it was foolish, but because nature turned out to be more nuanced than expected. For a long time, the wave picture of light did not merely dominate physics. It felt complete. It had history behind it, mathematics behind it, and experiment after experiment lining up in its favour. So when light began behaving in ways that did not fit that picture, the reaction was not excitement. It was confusion, resistance, and in some cases, quiet denial. The idea that light could behave like a particle did not arrive as a natural extension of existing theory. It arrived as a disruption, one that forced physicists to reconsider what it even means for something to be made of anything at all. The shift did not happen in a single dramatic moment. There was no announcement, no sudden consensus. Instead, it unfolded gradually, through a series of stubborn experimental results that refused to be explained away. Each one alone was troubling. Together they formed a pattern that could no longer be ignored. The strange day when light became a particle was not a day on the calendar, but a turning point in how reality itself was understood. One of the earliest warning signs came from something deceptively simple: heated objects glowing. Anyone who has watched a piece of metal heat up has seen this. First it darkens, then it glows red, then orange, then white. Classical physics attempted to describe this glow using wave theory. According to the equations, as an object gets hotter, it should emit more and more energy at higher frequencies. When physicists followed this logic to its conclusion, they encountered a disaster. The predicted energy output at high frequencies became infinite. This result, later called the ultraviolet catastrophe, was not just wrong, it was absurd. Nature, it turned out, was much more restrained. Experiments showed that the energy emitted by hot objects peaked at a certain frequency and then dropped off. There was no catastrophe. Something was limiting how energy could be distributed. To address this, Max Planck made a move that would later be recognized as revolutionary, though at the time it was almost apologetic. He suggested that energy exchange between matter and the electromagnetic radiation could only happen in discrete amounts. These amounts were proportional to the frequency of the radiation. Planck did not claim that light itself was made of particles. He treated quantization as a property of matter, interacting with waves. It was a mathematical fix, not a philosophical declaration, but it planted a seed. If energy exchange happened in chunks, then perhaps something about light itself was not as smooth as waves suggested. The situation became much harder to ignore with the photoelectric effect. When light shines on certain metals, electrons are ejected from the surface. Classical wave theory predicted that brighter light should eject more energetic electrons, regardless of colour. The experiment said otherwise. Below a certain frequency, no electrons were ejected at all, no matter how intense the light was. Above that frequency, electrons were ejected instantly, even at very low intensities. This behaviour was deeply unsettling. It suggested that light delivered its energy in all-or-nothing events. Either an electron received enough energy in one interaction, or it received nothing. There was no gradual accumulation, no slow shaking loose by a gentle wave. Albert Einstein took Planck's idea further than Planck himself was comfortable with. In 1905, he proposed that light consists of discrete packets of energy. Each packet carried an amount of energy proportional to its frequency. When one of these packets interacted with an electron, it transferred all its energy at once. If the energy was sufficient, the electron escaped. If not, nothing happened. This was a radical claim. It suggested that light, long understood as a wave spread out over space, sometimes behaved as if it were composed of localized entities. These entities were later named photons. At first, the idea was met with skepticism. Einstein was already proposing bold ideas about space and time, and this seemed like another step too far. What made the proposal difficult to accept was not just its novelty, but how deeply it conflicted with intuition. Waves distribute energy continuously. Particles deliver energy in discrete hits. Light appeared to be doing both, depending on the situation. This was not a minor inconsistency. It struck at the heart of classical physics, which relied on clear categories. As more experiments accumulated, the particle-like behaviour of light became undeniable. Compton scattering provided another key piece of evidence. When X-rays collided with electrons, the scattered light showed a change in wavelength that depended on the angle of scattering. This behaviour could be explained cleanly if light carried momentum, like a particle. Wave explanations struggled to reproduce the results without convoluted assumptions. Momentum had long been associated with mass and motion. The idea that something massless could carry momentum felt counterintuitive, yet the equations worked. Light could push electrons, it could impart recoil. It behaved as if it were delivering a tiny kick with each interaction. At this point, the question shifted. Light was no longer being asked to choose between being a wave or a particle. It was being forced to inhabit both roles. This was not a comfortable resolution. It did not satisfy classical expectations, but it matched reality. Calling photons particles turned out to be both helpful and misleading. Helpful because it captured the discrete nature of energy exchange. Misleading because photons are not particles in the everyday sense. They do not have hard edges. They do not follow well-defined paths until measured. They do not exist as little pellets travelling through space in the way early imagination might suggest. Instead, the photon emerged as a quantum object, something that defied classical classification. It could produce interference patterns like a wave, even when sent through an apparatus one at a time. Each photon seemed to interfere with itself, as if it explored multiple paths simultaneously before deciding where to land. This behaviour challenged not only the nature of light, but the nature of explanation itself. In classical physics, objects had properties whether or not they were observed. In quantum physics, measurement played an active role. The way you asked a question affected the answer you received. The strange daylight became a particle was therefore also the day physics had to confront the limits of classical thinking. The photon did not fit neatly into existing boxes. It forced the creation of a new framework, one in which fields, probabilities, and quantization coexisted uneasily. Over time, this framework matured into quantum electrodynamics, one of the most accurate theories ever developed. In this theory, light is described as excitations of the electromagnetic field. Photons are not tiny balls, but quantized modes of that field. They are the smallest possible disturbances that can carry energy and momentum. This description preserves the wave nature of light at large scales while accounting for its particle-like behavior and interactions. When light propagates freely, it behaves like a wave. When it interacts with matter, it behaves as if it consists of discrete units. Both descriptions are necessary. Neither alone is sufficient. What makes this transition particularly strange is that nothing about light itself changed. Light did not suddenly decide to become particulate. What changed was human understanding. Experiments reached a level of precision that exposed behaviors previously hidden. The universe did not reveal a new rule. It revealed the inadequacy of an old one. This realization has important consequences for the question of what a photon is made of. Particles in classical physics are made of matter. They have mass, occupy space, and persist over time. Photons do none of these things. They are not made of smaller bits. They are not assembled. They are created and absorbed as whole units. Thinking of photons as particles can be useful, but only if the word particle is stripped of its everyday meaning. A photon is not a tiny object flying through space like a grain of sand. It is a quantum of interaction, the smallest unit by which the electromagnetic field can exchange energy. The resistance to this idea was understandable. Physics had built enormous success on the assumption that waves and particles were fundamentally different. Light erased that boundary. It showed that nature does not respect the categories humans find comfortable. This discomfort extended beyond light. Once photons were accepted, electrons and other particles began exhibiting wave-like behavior as well. Matter itself could diffract, interfere, and exist in superpositions. The distinction between wave and particle became a matter of description, not identity. Yet light's transformation was the first crack. It was the moment when a phenomenon long considered well understood revealed a hidden depth. The smallest messenger in the universe turned out to be stranger than expected, not because it contained hidden parts, but because it refused to be reduced to a single classical picture. The phrase, "light became a particle," is therefore a shorthand, not a literal statement. Light did not abandon its wave nature. It expanded its identity. It showed that the fundamental level of reality operates by rules that do not map cleanly onto everyday experience. As understanding deepened, physicists learned to speak more carefully. They stopped asking whether light is a wave or a particle, and began asking under what conditions each description applies. The answer depends on what is being measured and how. This shift has echoes throughout modern science. It teaches caution about assuming that familiar categories apply universally. It suggests that asking what something is made of may not always be the right question. Sometimes, the better question is how something behaves and what rules constrain that behavior. Encountering a photon for the first time is not like meeting a new object. There is no shape to recognize, no surface to imagine, no weight to assign. Instead, it is more like realizing that something you thought you already understood has been quietly operating under different rules all along. The word photon feels concrete, almost friendly, as if it names a tiny thing you could picture moving from place to place. But the first real meeting with a photon, in the scientific sense, is usually an encounter with discomfort, because it forces you to let go of several assumptions at once. For many students of physics, that meeting happens not through a direct observation, but through equations, experiments, and contradictions. You learn that light can eject electrons from metal, but only under specific conditions. You learn that light can interfere with itself even when sent one unit at a time. You learn that light carries momentum despite having no mass. Each of these facts alone is strange. Together they make it clear that the photon is not a classical object wearing a new name. One of the first things that becomes apparent is that you cannot observe a photon in isolation in the way you might observe a grain of dust or a drop of water. A photon is never seen directly. It is always inferred from an interaction. You know a photon was there because an electron moved, because a detector clicked, because a chemical reaction occurred in your retina. The photon announces itself only by disappearing. This is not a poetic exaggeration. Absorption is how photons are detected. The act of measurement is also the act of destruction. This alone sets photons apart from ordinary matter. You can look at an electron without destroying it. You can trap atoms, weigh them, manipulate them, and release them again. A photon does not allow this. It does not sit still. It does not wait to be examined. Its entire existence is bound up in motion and interaction. The moment it stops moving, it stops being a photon. This creates an immediate challenge for intuition. If something cannot be isolated, stored easily, or examined without annihilation, what does it mean to say it exists at all? The answer physics gives is practical rather than philosophical. A photon exists because its effects are consistent, measurable, and repeatable. You can predict how it will behave statistically. You can calculate the probability of where it will be detected. You can build technologies that rely on those predictions. Existence, in this context, is defined operationally. When physicists first began speaking seriously about photons, this operational view was essential. The photon was not introduced as a tiny bead of light flying through space. It was introduced as the smallest unit of electromagnetic energy exchange that could not be divided further. It was a bookkeeping device that turned out to describe reality remarkably well. Meeting the photon, then, often begins with energy. A photon has energy given by a simple relation. Energy equals Planck's constant multiplied by frequency. This formula looks harmless, but it carries profound implications. It tells you that energy is not something light carries continuously. It comes in indivisible portions. You can have 0 photons, 1 photon, 2 photons, but not half a photon. This discreteness shows up most clearly in low-light situations. If you dim a light source enough, it does not become infinitely faint in a smooth way. Instead, detection becomes sporadic. Individual events stand out. A detector clicks once, then waits, then clicks again. Each click corresponds to a single photon being absorbed. No click corresponds to no photon. There is no partial click. At this stage, many people try to imagine photons as tiny bullets. This is understandable, but it leads to confusion quickly. A bullet has a trajectory. It has a position at every moment in time. A photon does not behave this way. If you try to assign it a precise position, you lose information about its momentum. If you try to pin down its momentum precisely, its position becomes spread out. This is not a limitation of instruments, it is a fundamental feature of quantum behavior. The first real meeting with a photon therefore often involves probability rather than certainty. You stop asking where the photon is and start asking where it is likely to be detected. You stop imagining a path and start calculating distributions. This shift can feel unsettling because it replaces a picture with a rule. A particularly striking demonstration of this comes from single photon interference experiments. When photons are sent through a double-slit apparatus one at a time, each photon is detected as a single localized event on a screen. There is no smear, no wave-like splash, and yet, over time, an interference pattern emerges. Bright and dark bands appear, exactly as predicted by wave theory. This means that each photon somehow behaves as if it passed through both slits, interfered with itself, and then chose a single location to be detected. Trying to picture this process using everyday imagery quickly leads to contradictions. The photon is not splitting into pieces. It is not choosing randomly in a classical sense. It is following rules that do not resemble macroscopic behavior. Meeting the photon, then, often requires abandoning the idea that physical reality must be picturable in familiar terms. Instead, you learn to trust mathematical structure and experimental outcomes. The photon becomes something you work with rather than something you visualize. Another surprising aspect encountered early is that photons do not experience time. According to special relativity, time dilation increases as speed approaches the speed of light. At the speed of light, the passage of time effectively vanishes. While it is not meaningful to speak of a photon's perspective in a strict sense, the mathematics tells us that there is no elapsed proper time along a photon's path. This has strange implications. A photon emitted from a distant galaxy and absorbed by a telescope on Earth does not age. From emission to absorption, no time passes in its own frame. The journey that takes billions of years for the universe takes no time at all for the photon. This makes it difficult to treat photons as objects persisting through time. They are better understood as links between events. This event-based view becomes more prominent as you learn about quantum field theory. In that framework, photons are excitations of the electromagnetic field. The field exists everywhere, even in empty space. When it is excited in a particular way, a photon is said to exist. When that excitation is absorbed, the photon ceases to exist. Crucially, the photon is not made of the field as a substance. The field is not material in the classical sense. It does not have parts. It does not consist of smaller building blocks. It is a mathematical entity that assigns values to every point in space and time. The photon is a quantized change in that entity. This reframes the question of composition entirely. Asking what a photon is made of becomes like asking what a vibration is made of. A vibration is not made of smaller vibrations. It is a pattern of motion. Similarly, a photon is a pattern of excitation. This does not mean photons are vague or undefined. On the contrary, their properties are precisely specified. A photon has a well-defined energy, momentum, and polarization. Polarization describes the orientation of the oscillating electric and magnetic fields associated with the photon. This property can be manipulated, filtered, and measured with high accuracy. Polarization is another place where particle intuition struggles. You might be tempted to imagine a photon spinning like a tiny top. That image fails quickly. Photon spin, more accurately called helicity, is a quantum property that does not correspond to literal rotation. It describes how the electromagnetic field twists as the photon propagates. Again, the photon resists being turned into a tiny mechanical object. Meeting the photon also involves encountering the idea that photons are identical. Unlike macroscopic objects, photons of the same frequency, polarization, and direction are indistinguishable. There is no label you can attach to one photon to tell it apart from another. This indistinguishability has real consequences. It underlies phenomena like laser coherence and Bose-Einstein statistics for photons. At first, this can feel abstract, but it becomes concrete when you consider lasers. A laser produces light that is highly coherent, meaning the photons are in step with one another. They share the same frequency, phase, and direction. This collective behavior emerges precisely because photons do not retain individual identities. They act as unified excitation of the field. This collective aspect also appears in thermal radiation. The glow of a warm object is not produced by individually labelled photons with personal histories. It is produced by a statistical distribution of photon energies governed by temperature. The photons are interchangeable carriers of energy, not unique messengers with memory. Another moment of realization often comes when learning that photons can be created and destroyed freely, as long as energy and momentum are conserved. Unlike electrons, which are conserved in number under ordinary conditions, photons can appear and vanish. An atom can emit a photon. That photon can be absorbed by another atom. No photon number conservation law is violated. This reinforces the idea that photons are not building blocks of matter. They are not constituents. They are mediators. They exist to transfer energy and momentum between other systems. Once that transfer is complete, the photon has no further role. This mediator role is especially clear in how photons mediate the electromagnetic force. In quantum electrodynamics, charged particles interact by exchanging photons. These photons are often virtual, meaning they cannot be directly detected and do not obey the usual energy-momentum relations. They exist only within the mathematics of interactions. Meeting virtual photons is even more disorienting than meeting real ones. Virtual photons cannot be observed. They cannot be isolated. They exist only as internal elements of calculations. Yet their effects are measurable. The electromagnetic force works exactly as predicted by their exchange. This raises an important distinction. Not all photons are the same in how they appear in theory. Real photons are those that can be detected as free radiation. Virtual photons are internal carriers of force. Both arise from the same field. Both are described by the same underlying framework. The difference lies in how they are constrained by conservation laws. Understanding this distinction helps clarify why asking what a photon is made of can be misleading. Photons are not objects assembled from parts. They are manifestations of interactions governed by rules. They appear where those rules allow them to appear and disappear where those rules permit. At this stage, many people experience a shift in how they think about physical reality. The idea that everything must be made of smaller things gives way to the idea that some things are fundamental processes. Photons belong to this second category. They are not stuff. They are events that propagate. This does not make them less real. If anything, it makes them more deeply embedded in the structure of the universe. Every electromagnetic interaction, from chemical bonds to radio transmissions to starlight, depends on photons behaving exactly as they do. Their lack of internal structure is not a deficiency. It is what allows them to be universal messengers. Meeting the photon for the first time, then, is not about seeing something new. It is about realizing that reality does not always match the categories our minds prefer. The photon forces you to accept that something can be real without being solid, persistent without aging, influential without mass. As understanding deepens, the initial discomfort often gives way to a kind of respect. The photon does not pretend to be simpler than it is. It follows its rules consistently, even when those rules feel counterintuitive. It carries information across the universe without regard for human expectations. At some point, once the initial surprise of the photon wears off, a quieter and more unsettling question begins to surface. If a photon is not a tiny object, not a bead of light, not something you can point to or imagine resting on a surface, then does it have substance at all? Is there anything there in the sense we usually mean when we talk about things existing? Or is the photon merely a convenient name for a mathematical effect, a shorthand for interactions that don't truly involve a thing moving through space? This question is not philosophical decoration. It goes straight to the heart of how modern physics understands reality. For most of human history, substance meant matter, something solid or fluid, something that occupies space, something you could, at least in principle, hold, cut, weigh, or divide. Even gases, invisible as they are, still press on surfaces and resist compression. Substance was tied to mass, to inertia, to persistence through time. Photons immediately challenge this picture. They have no rest mass. You cannot pile them up to make something heavier. You cannot trap them easily and weigh the container before and after. They always move. They do not linger. If substance requires mass at rest, photons fail the test right away. Yet dismissing them as insubstantial feels wrong. Light exerts pressure. It transfers momentum. It heats surfaces. It triggers chemical reactions. It powers photosynthesis, drives climate, and allows vision. These are not abstract effects. They're physical consequences. Something without substance in the everyday sense should not be able to do all that. To make sense of this, it helps to separate two ideas that are often quietly merged. One is substance as material composition, the other is substance as physical reality. Matter satisfies both. Photons satisfy only one. A photon has no material composition. It is not made of smaller bits. There are no constituent particles hiding inside it. As far as current physics can tell, photons are elementary. They cannot be split into more fundamental pieces. In that sense, they lack substance in the way atoms or molecules have substance. But photons are unquestionably physically real. They obey precise laws. They produce measurable effects. They carry conserved quantities like energy and momentum. They participate in interactions that shape the behavior of matter itself. Physical reality does not require material composition. It requires consistency, predictability, and causal influence. Photons meet all of these criteria. The confusion often arises because everyday language evolved to describe macroscopic objects, not fundamental processes. When we ask whether something has substance, we usually mean whether it is made of matter. Physics, however, has learned that not everything real is made of matter. Fields are a prime example. An electric field is not made of particles, yet it exerts forces. A magnetic field curves charged particle trajectories. Gravitational fields shape the motion of planets. These fields are not substances you can scoop up, but they are as real as anything else in physics. The photon fits naturally into this picture once you stop thinking of it as a thing and start thinking of it as an excitation. In quantum field theory, every type of particle corresponds to a field that exists everywhere. The electromagnetic field fills all of space. Even in a perfect vacuum, it is still there, capable of being excited. A photon is one such excitation. It is not a piece of the field carved out and sent travelling. It is the field temporarily doing something specific. Asking what substance a photon is made of is therefore similar to asking what substance a wave on the ocean is made of. The wave is not made of water molecules in the way a bucket of water is. It is a pattern of motion that involves water, but is not itself a material object. This analogy, while imperfect, helps clarify the relationship. The electromagnetic field is not water, and photons are not literal ripples. But the idea that a pattern can be real without being made of stuff carries over. The wave exists because the underlying medium supports it. The photon exists because the field supports quantized excitations. However, the analogy also breaks down in an important way. Water waves require water molecules. Remove the water and the wave cannot exist. Photons do not require a material medium. They exist even in empty space. This tells us that the electromagnetic field itself is fundamental, not emergent from matter. This leads to a subtle but important conclusion. The photon's lack of substance is not a weakness. It reflects the fact that substance at the most fundamental level is not the right concept. The universe is not built from little solid blocks stacked together. It is built from fields and interactions, from rules that govern how energy and momentum move. Still, the urge to ask what something is made of is strong, because it has worked so well elsewhere. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. Each step reveals deeper structure. With photons, that ladder stops. There is no smaller rung. The photon is not made of quarks. It is not made of strings, at least not in any experimentally supported way. It is not made of energy as a substance. Energy is a property, not a material. This can feel unsatisfying, but it is also revealing. It suggests that the search for substance has limits. Some elements of reality are defined not by what they're made of, but by how they behave. Another way to approach the question is through interaction. Matter interacts by colliding, binding, and exchanging forces. Photons interact by being absorbed or emitted. When a photon is absorbed, its energy and momentum are transferred entirely to the absorbing system. There is no residue. The photon does not leave behind fragments. This all-or-nothing behavior reinforces the idea that photons are not containers of stuff. They are events with precise consequences. When the event ends, nothing remains of the photon itself. Even momentum, which feels like something tangible, does not imply substance. Momentum is a conserved quantity associated with motion and symmetry. A photon has momentum because the electromagnetic field carries momentum. When a photon strikes a surface, it transfers that momentum, producing pressure. This does not require mass. It requires consistency in the laws governing motion. Light pressure, once thought negligible, has been measured and harnessed. Solar sails rely on it. Laser cooling techniques use photon momentum to slow atoms. These applications do not turn photons into substance. They use the rules photons obey. Another source of confusion comes from the word particle itself. In everyday language, particles are tiny bits of matter. In physics, the word has broadened. A particle is now understood as a discrete excitation that can be counted and tracked statistically. Under this definition, photons qualify. They are countable. They are discrete. But they are not material in the classical sense. This distinction becomes clearer when comparing photons to other elementary particles. Electrons have mass. They can be localized more easily. They persist over time. They are conserved in number under ordinary conditions. Photons differ on all counts. They are massless, delocalized, temporary, and not conserved in number. Yet both are considered particles because both appear as quantized excitations of fields. Substance, then, is no longer the defining feature of particles. Quantization is. The idea that photons lack substance also connects to their relationship with time. A material object exists through time. It has a history. It ages. A photon does not experience time. From emission to absorption, there is no internal clock ticking. This makes it difficult to assign the photon an identity that persists. Without persistence, substance loses its meaning. Substance implies something that endures. The photon exists only as long as it is in motion, and even that existence is not something it experiences. This does not mean photons are illusions. Illusions do not exert force, do not heat surfaces, do not encode information. Photons do all of these things reliably. Their reality is operational rather than material. Information provides another useful lens. Photons are excellent carriers of information. The frequency of a photon tells you about the energy transition that produced it. Its polarization can encode data. Its direction carries spatial information. In modern technology, photons carry vast streams of digital information through fiber optic cables. Information itself is not a substance. You cannot weigh a message separately from its carrier. Yet information has physical consequences. It requires energy to transmit. It obeys physical limits. Photons are the carriers, not the content, but the fact that they can carry information reinforces their role as functional rather than material entities. Some physicists go further and argue that information, not substance, is the most fundamental concept. In this view, photons are units of information transfer governed by physical law. Whether or not one accepts this interpretation, it highlights how far the photon sits from classical ideas of material composition. It is also worth noting that photons interact very weakly with one another. Two beams of light can cross paths without disturbance. This is another reason photons do not behave like material objects. Matter tends to collide, scatter, and bind. Photons pass through each other as if the other were not there. This weak self-interaction is not absolute. Under extreme conditions, photons can interact indirectly through higher-order quantum effects. But these interactions are rare and subtle. For most practical purposes, photons are transparent to one another. Transparency to self-interaction further erodes the idea of substance. Substance usually implies solidity, or at least resistance. Photons offer almost none. They are the ultimate passers-by. At this point, it becomes reasonable to answer the question directly. Does a photon have substance at all? If substance means material composition, mass, persistence, and internal structure, then no, it does not. A photon has no substance in that sense. If substance means physical reality, causal power, and participation in the laws of nature, then yes, absolutely. Photons are as real as anything else in physics. This dual answer is unsatisfying only if one insists on using everyday language to describe fundamental phenomena. Physics has learned, sometimes reluctantly, that reality does not owe us intuitive categories. The photon sits at the boundary where those categories break down. It is not matter. It is not empty space. It is not a thing in the ordinary sense. It is a rule made manifest, an interaction packaged into the smallest allowed unit. Understanding this does not require abandoning clarity. It requires shifting what clarity means. Instead of picturing substance, you focus on behavior. Instead of asking what something is made of, you ask what it does and what constraints it obeys. At first glance, the phrase sounds like a contradiction. Energy without mass, motion without weight. In everyday experience, energy is tied to things that have heft. A moving car carries energy because it has mass. A thrown stone has momentum because it is heavy enough to resist changes in motion. Even wind, which feels light, is made of air molecules with mass rushing past you. Motion and mass seem inseparable, stitched together by intuition built from living in a world of solid objects. And yet photons break that link completely. They move, they transfer energy, they exert force, they change the behavior of matter, all without possessing mass at rest. This is not a technical loophole or a semantic trick. It is a core feature of how light exists, and understanding it requires loosening some deeply ingrained assumptions about what motion and energy actually mean. To begin untangling this, it helps to look at how mass usually enters the picture. In classical physics, mass plays several roles at once. It measures how much matter an object contains. It determines how strongly gravity pulls on it. It sets how resistant the object is to changes in motion. Because these roles are bundled together in everyday situations, mass feels like a single obvious property. Photons slip through that bundle. They have no rest mass, meaning there is no frame of reference in which a photon is stationary. You cannot slow a photon down, you cannot bring it to rest. Its speed is fixed by the structure of spacetime itself. Because of this, the usual definition of mass as resistance to acceleration simply does not apply. A photon does not resist acceleration, because it cannot be accelerated in the first place. This does not mean photons are exempt from physics, quite the opposite. Their behavior is governed by some of the most precisely tested laws we have, but those laws are not the ones that intuition reaches for first. The key shift comes from understanding that energy and momentum do not require mass in the way we once thought. In classical mechanics, momentum is defined as mass times velocity. Set the mass to zero and momentum disappears. This formula works beautifully for everyday objects, but it's not the final word. Relativity changes the definition. In relativistic physics, energy and momentum are part of a single structure. For objects with mass, energy includes both rest energy and kinetic energy. For objects without mass, all energy is kinetic in a sense, but it does not vanish. Instead, it is tied directly to motion at the speed of light. For photons, momentum is proportional to energy divided by the speed of light. This relationship has been confirmed countless times. When a photon strikes an object, it transfers momentum. The object recoils. This recoil has been measured in laboratories with extreme precision. Light pressure is not theoretical. It is real, measurable, and exploitable. This is one of the earliest clues that weight and influence are not the same thing. Weight is tied to gravitational mass. Influence is tied to momentum and energy transfer. Photons lack the former, but possess the latter. The idea that something weightless can push on something heavy feels strange until you remember that pressure does not require weight. Pressure is force distributed over area. A gas exerts pressure because its molecules collide with surfaces. A photon exerts pressure because its momentum changes when it is absorbed or reflected. In both cases, force arises from momentum transfer, not from weight. When sunlight strikes a surface and is absorbed, the photons deliver their momentum to that surface. When sunlight reflects, the momentum change is even larger. Multiply this effect by an enormous number of photons, and the force becomes noticeable. This is the principle behind solar sails, where spacecraft are propelled by sunlight alone. No fuel, no exhaust, just momentum exchange. This realization forces a re-evaluation of what motion means. Motion does not require mass, it requires change. A photon represents change propagating through the electromagnetic field. That propagation carries energy and momentum even though no material object is moving along with it. Another place where this becomes clear is gravity. Photons are affected by gravity. Light bends around massive objects. Gravitational lensing causes distant stars and galaxies to appear distorted when their light passes near massive bodies. This bending is not because photons have weight in the classical sense. It is because gravity curves space-time, and photons follow the geometry of that curvature. This distinction matters. Photons do not fall toward massive objects the way stones do. They follow the straightest possible paths in a curved space-time. The result looks like attraction, but the mechanism is different. Once again, mass is not the essential ingredient. Even more intriguing is the fact that photons themselves contribute to gravity. Energy gravitates. Momentum gravitates. A box filled with light weighs more than an empty box. This is not a metaphor. It follows directly from general relativity. If you trap photons inside a perfectly reflective container, the total energy of the system increases, and so does its gravitational mass. This creates a subtle but important point. While individual photons have no rest mass, systems containing photons can have mass. The mass is not located in the photons as objects. It arises from the total energy content of the system. Mass, in this deeper sense, is not a substance but a measure of energy and its relation to space-time. Once this is understood, the idea of energy without mass becomes less paradoxical. Energy is not something stored inside matter like water in a bottle. Energy is a property of systems, a measure of their capacity to cause change. Photons are pure carriers of that property. They are energy in transit. Motion without weight follows naturally. Weight is the force experienced in a gravitational field. Photons do not experience weight because they do not have rest mass to respond that way. Yet they move relentlessly at the same speed in all inertial frames, carrying influence wherever they go. This raises another question that often surfaces at this stage. If photons have no mass, how can they have energy? In everyday language, energy is often associated with effort, exertion, and fuel, all of which involve matter. Physics, however, defines energy more abstractly. Energy is associated with symmetry. Specifically, it is conserved because the laws of physics do not change over time. Photons inherit energy because the electromagnetic field supports excitations that obey this conservation. The energy of a photon is tied to its frequency. Higher frequency means more rapid oscillation of the field, and therefore more energy. Lower frequency means less. This energy is not stored in a substance. It is not located in a tiny container. It is a feature of the excitation itself. The photon does not carry energy the way a truck carries cargo. The photon is energy arranged in a specific quantized form. The absence of mass also explains why photons always travel at the same speed. Objects with mass require energy to accelerate. As their speed increases, so does their resistance to further acceleration. For a photon, there is no rest state to accelerate from. Its existence is inseparable from motion at the speed of light. This speed is not a limit imposed on photons. It is their natural state. This constancy has deep implications. Because photons always move at the same speed, they provide a universal standard. The speed of light becomes a fundamental constant, not because light is special, but because spacetime is structured in such a way that massless excitations propagate at that speed. From this perspective, photons are not exceptions to the rules. They reveal the rules. They show what motion looks like when mass is removed from the equation entirely. The idea of motion without weight also clarifies why photons cannot be slowed down by friction or resistance in empty space. There is nothing for them to push against. In a medium like glass or water, light appears to slow down, but this is a collective effect involving repeated absorption and re-emission by atoms. The individual photons between interactions still move at the same speed. The delay arises from the interactions, not from a change in photon speed. This distinction matters because it reinforces the idea that photons are not objects ploughing through a medium. They are events linking interactions. When a photon moves through a medium, it is not the same photon being slowed. It is a sequence of interactions producing an overall delay. Energy without mass also explains why photons can be created and destroyed so freely. Creating mass requires specific conditions and conservation laws. Creating photons requires only energy. An excited atom can emit a photon. A charged particle can radiate photons when accelerated. Matter and photons interconvert constantly. This interconversion highlights another difference between photons and material particles. Matter particles carry identity. An electron remains an electron. A photon does not persist in the same way. It exists only as long as it is transferring energy. Because photons lack mass, they also lack a preferred frame of reference. There is no meaningful way to ask what a photon's rest frame looks like. This limits how we can talk about their perspective, but it also protects consistency. Allowing a photon rest frame would break the structure of relativity. In practical terms, this means photons do not age, do not decay, and do not carry internal clocks. Their lack of mass is tied directly to their lack of internal structure. There is nothing inside a photon that could tick or change independently of its motion. This brings the discussion back to substance. Mass is often taken as evidence of substance. Remove mass, and the thing feels ghost-like. But photons are not ghosts. They obey rules with extraordinary precision. They influence matter reliably. They shape the universe on every scale. The mistake lies in equating substance with importance. Photons show that influence does not require weight, and that motion does not require mass. The universe is not built solely from heavy things bumping into one another. It is built from interactions, from exchanges, from fields and excitations that do not resemble everyday objects. This understanding reshapes how we think about light. Light is not something that fills space like fog. It is not something that flows like a fluid. It is not something that travels like a projectile. It is energy propagating under strict constraints, always at the same speed, always in discrete units. Colour feels immediate. You see it without effort, without calculation, without training. Blue sky, green leaves, warm amber light in the evening. It arrives as a quality of experience, not as a number or a measurement. And yet, beneath that familiarity lies one of the most precise and unforgiving relationships in all of physics. When a photon carries colour, it does so through frequency, and that frequency is not a suggestion or a range. It is exact. Understanding how photons carry colour means stepping away from subjective experience and into a world where oscillations, energy and interaction replace names like red and violet. To begin, it helps to separate two ideas that are often blended together. Colour, as we experience it, is a product of biology and perception. Colour, as carried by photons, is a physical property tied to frequency and wavelength. The two are related, but they are not the same thing. A photon does not know it is red. It does not contain redness. It carries a frequency, and your nervous system translates that frequency into an experience you label as colour. Frequency refers to how rapidly the electromagnetic field oscillates as the photon propagates. This oscillation is not something happening inside the photon like a ticking mechanism. It is a description of how the field varies in space and time. A higher frequency means the field changes more rapidly. A lower frequency means it changes more slowly. That single parameter determines how much energy the photon carries, and consequently what colour it may be perceived as. The relationship between energy and frequency is direct and unavoidable. Double the frequency, and you double the energy of the photon. There is no adjustment factor, no dependence on context. This is why ultraviolet photons carry more energy than visible light photons, and why gamma rays carry vastly more energy still. Colour, then, is not decoration. It is a signal of energy scale. This is already a departure from everyday intuition. In daily life, colour feels cosmetic. It feels optional. You can paint a wall a different colour without changing what the wall is made of. But for photons, colour is identity. Change the frequency, and you have changed the photon's energy, its interactions and its consequences. A photon that appears red and one that appears blue are not the same kind of thing behaving differently. They are fundamentally different excitations of the electromagnetic field. Wavelength often enters the conversation here, and it is important to be precise. Frequency and wavelength are linked by the speed of light. In empty space, all photons travel at the same speed. This means that higher frequency photons necessarily have shorter wavelengths, and lower frequency photons have longer wavelengths. Wavelength is the spatial separation between repeating features of the wave description. Frequency is the temporal rate of oscillation. There are two ways of describing the same underlying behaviour. Colour is usually discussed in terms of wavelength, because it maps conveniently onto visual perception. The visible spectrum ranges from roughly 400 nanometers to 700 nanometers. But frequency is the more fundamental quantity, because it does not change when light enters different media. Wavelength does. When light passes from air into glass or water, its wavelength shortens. The speed of light in the medium is lower than in vacuum, so the spatial pattern compresses, but the frequency remains unchanged. This is crucial. The photon does not lose or gain energy simply by entering a medium. Its frequency stays fixed, and with it, its colour as perceived by your eyes. This invariance of frequency tells us something important about how photons carry colour. Colour is not a property imposed by the environment. It is intrinsic to the photon's mode of excitation. The medium can influence how the photon propagates, but not what frequency it has. Another layer of subtlety appears when considering how photons are created. Photons do not emerge with arbitrary frequencies. They are produced through specific processes that impose strict constraints. When an atom emits a photon, the frequency of that photon corresponds exactly to the energy difference between two electronic states. This is not approximate. It is precise to many decimal places. This precision is why atomic spectra are so useful. Each element produces a characteristic set of spectral lines. These lines are fingerprints. They allow astronomers to identify the composition of distant stars by analysing the light they emit. The photons arriving at Earth carry information about atomic transitions that occurred light years away, and they do so without distortion of frequency. This again highlights the messenger role of photons. Frequency is the message. Colour is how that message is interpreted. It is tempting at this point to imagine photons as vibrating objects, like tiny tuning forks oscillating at different rates. This image is misleading. The photon is not a little thing shaking back and forth. The oscillation belongs to the electromagnetic field, not to a material component of the photon. The photon is the quantized excitation of that oscillation. In quantum field theory, the electromagnetic field has modes, each corresponding to a particular frequency and polarization. A photon is an excitation of one of these modes. The frequency is not something the photon carries around as cargo. It is the defining feature of the excitation itself. This distinction matters because it explains why photons of different frequencies are fundamentally different, not just differently coloured versions of the same object. A red photon and a blue photon are excitations of different modes. They interact differently with matter. They deposit different amounts of energy. They trigger different electronic transitions. Your eye makes use of this fact. The photoreceptor cells in your retina are sensitive to different ranges of frequency. They do not detect color directly. They respond to energy. The pattern of activation across these cells is interpreted by your brain as color. This interpretation is remarkably stable, but it is not universal. Different species perceive different ranges of frequency. Some animals see ultraviolet light, others see infrared. The photons are the same. The biology changes the experience. This brings up an important point. Color does not exist in photons. It exists in interactions. A photon of a given frequency interacting with a particular sensory system produces a color experience. Without an observer or a detector, the photon simply has a frequency. Detectors built by physicists reflect this reality. A photodetector does not see red or blue. It responds when a photon deposits energy. The response depends on whether the energy matches the detector's sensitivity. Color is reconstructed after the fact based on frequency. Understanding this helps prevent a common misconception. Photons do not change color as they travel through empty space. They do not fade or drift in frequency. In an expanding universe, photons do experience redshift, but this is not because they lose energy in the usual sense. It is because spacetime itself is stretching, altering the relationship between emission and detection, and the photon's frequency relative to the observer changes because the geometry of spacetime changes. This cosmological redshift is sometimes described as photons losing energy over time. That language can be misleading. Energy conservation in general relativity is subtle. What matters is that frequency, as measured by different observers, can differ depending on relative motion and spacetime curvature. The photon itself does not degrade. Another misconception arises from thinking of frequency as something localized. In classical waves, frequency is defined over many oscillations. A photon, especially a short pulse, may not have a perfectly defined frequency. There is a trade-off between temporal localization and frequency precision. A photon emitted in a very brief event has a spread of frequencies. This is not noise or imperfection. It is a fundamental property of waves and quantum systems. Frequency is not a label stamped on the photon. It is a property of the excitation over time. This again reinforces the idea that photons are not objects with fixed internal attributes. Their properties emerge from how they are created and measured. Color also connects to another property, momentum. A photon's momentum depends on its frequency. Higher frequency photons carry more momentum. This is why blue light can exert more pressure than red light at the same intensity. Momentum transfer is frequency dependent. This has practical consequences. Laser cooling techniques use photons to slow atoms. By choosing the frequency carefully, physicists can ensure that photons are absorbed preferentially when atoms move toward the light source, reducing their motion. The color of the light is not aesthetic, it is functional. At this stage, it becomes clear that color is not an added feature layered on top of photons. It is a manifestation of their most basic physical parameter. Frequency determines energy. Energy determines interaction. Interaction determines consequence. This tight coupling explains why there is no such thing as a photon without frequency. A photon with zero frequency would have zero energy. Such an excitation does not exist. Even the lowest energy photons, radio waves with wavelengths longer than planets, still carry finite energy. This also explains why photons do not gradually bleed energy as they travel. There is no mechanism for partial energy loss in empty space. A photon either interacts and transfers its energy or it does not. There is no friction to slow it down. Frequency remains fixed until interaction. When interaction does occur, frequency determines what happens. A photon whose energy matches an allowed transition can be absorbed. One that does not will pass through or scatter. Matter is selective. Photons announce themselves through frequency, and matter responds accordingly. This selectivity underlies transparency and opacity. Glass is transparent to visible light because the photon's frequencies do not match the energy gaps of electrons in the glass. Ultraviolet photons with higher frequency can be absorbed, making glass opaque to them. Infrared photons may be absorbed as heat. Same material, different response, entirely determined by photon frequency. Seen this way, colour is not decoration but compatibility. It is a measure of which interactions are allowed. At the deepest level, frequency reflects how the electromagnetic field is excited. Different frequencies correspond to different normal modes of the field. These modes are independent. A photon in one mode cannot gradually morph into another without interaction. There is no internal dial that turns red into blue. This independence is why colour mixing works the way it does. Mixing red and green light produces yellow perception, not because photons blend, but because multiple frequencies stimulate different receptors. The photons remain distinct. There is no yellow photon created by mixing red and green light. This distinction often surprises people, but it reinforces the idea that photons carry frequency, not colour. Colour is constructed. As understanding deepens, it becomes clear that frequency is one of the most fundamental attributes of a photon. It defines energy, momentum, interaction, and perception. It is not an accessory, it is the message. And yet, even here, there is no substance underneath. Frequency is not a material component. It is a pattern. It is a rate. It is a description of how something changes. The photon carries this pattern across space without carrying matter along with it. Spin is a word that invites misunderstanding the moment it appears. It sounds mechanical, almost comforting, as if it refers to something rotating the way a top spins on a table or a planet turns on its axis. When applied to photons, that intuition becomes a trap. Photons do not spin in space like tiny balls. There is no surface rotating, no internal mass turning around a centre, and yet spin is one of the defining properties of a photon, just as essential as energy or frequency. Closely tied to it is polarization, a feature that gives light a kind of orientation without giving it shape. Together, spin and polarization reveal how photons can possess structure without substance, orientation without extension, and identity without parts. To understand what spin means for a photon, it helps to step away from imagery and towards symmetry. In physics, spin is not primarily about rotation. It is about how something behaves under rotation. If you rotate a system and nothing changes, that tells you something. If rotating it produces a measurable difference, that tells you something else. Spin is a way of classifying how a quantum entity responds to rotations in space. For material particles like electrons, spin can be loosely associated with angular momentum, though even there the classical picture fails quickly. For photons, the situation is even more abstract. A photon has spin equal to 1 in units of Planck's reduced constant, but this does not mean it spins once per unit time or anything remotely like that. It means that the photon belongs to a class of quantum excitations with specific rotational symmetry properties. Because photons are massless, their spin behaves differently than the spin of massive particles. A massive particle can have its spin oriented in many directions relative to its motion. A photon cannot. Its spin is locked to its direction of travel. This constraint removes degrees of freedom and leads directly to polarization. Polarization describes the orientation of the electromagnetic field associated with a photon. Even though photons are not little vibrating strings, the electromagnetic field they represent has direction. The electric field oscillates in a plane perpendicular to the direction of propagation. That plane can be oriented in different ways. Those orientations are what we call polarization states. Linear polarization occurs when the electric field oscillates back and forth along a fixed direction. Circular polarization occurs when the direction of oscillation rotates as the photon moves forward, tracing out a helix. There are also elliptical polarizations, which are intermediate cases. These are not decorative labels. They correspond to measurable differences in how light interacts with matter. The key point is that polarization is not something added to a photon like an accessory. It is an intrinsic degree of freedom. A photon is always polarized in some way, even if that polarization is random or unmeasured. There is no unpolarized photon in the fundamental sense. Unpolarized light is a statistical mixture of photons with different polarizations. This subtlety matters because it reinforces the idea that photons carry structure without carrying substance. Polarization encodes orientation information without requiring an oriented object. There is no arrow attached to the photon pointing in a particular direction. The orientation exists in the field description, not in a material frame. Spin enters this picture through helicity, which is the projection of spin along the direction of motion. For photons, helicity can take only two values. These correspond to left-handed and right-handed circular polarization. There are no other options. This discreteness is not a limitation of technology. It is a fundamental property of massless spin-1 particles. This binary nature of photon helicity has deep consequences. It explains why photons always move at the speed of light. It explains why they have only two polarization states rather than three. It also ties into how photons interact with other particles and fields. At this point, it is tempting to imagine helicity as a kind of twist, like a corkscrew motion. This image can be helpful as a rough guide, but it should not be taken literally. There is no physical rod twisting through space. The twist refers to how the electromagnetic field transforms under rotations. One way to see the physical reality of polarization is through filters. A polarizing filter allows light of one polarization to pass while blocking others. When unpolarized light passes through such a filter, its intensity is reduced because only photons with compatible polarization states are transmitted. Rotate the filter, and the transmitted intensity changes. Nothing about the photons themselves changes except whether they are absorbed or allowed through. The filter is not sorting photons by color or energy. It is sorting by orientation. This is remarkable when you think about it carefully. Something without shape is being filtered by orientation. This works because polarization is not shape. It is compatibility between field configurations. The filter's internal structure interacts with the electric field component of the photon. If the field oscillation aligns with the allowed direction, interaction proceeds. If not, absorption occurs. Spin and polarization also play a role in conservation laws. When a photon is emitted or absorbed, angular momentum must be conserved. The spin of the photon contributes to this balance. This is not optional. It is enforced by symmetry. For example, when an atom emits a photon, the change in the atom's angular momentum must match the spin of the photon. Selection rules govern which transitions are allowed based on these constraints. These rules are not arbitrary. They arise from the rotational symmetries of the system. This brings us back to substance. Angular momentum is often associated with rotation of mass. But photons carry angular momentum without mass. Once again, mass is not the essential ingredient. Symmetry is. Photons can even carry orbital angular momentum in addition to spin. This is a more subtle effect where the electromagnetic field has a twisted spatial structure. Light beams with orbital angular momentum can exert torque on microscopic objects, causing them to rotate. This has been demonstrated experimentally and used in optical manipulation. Here again, light influences matter without being matter. It transfers angular momentum without having a rotating body. The angular momentum resides in the field configuration. These effects make it clear that photons are not featureless. They are structured excitations. Their structure, however, is not built from parts. It is encoded in how the field behaves. Another important aspect of polarization is that it can be entangled. Two photons can be created in a joint state, where their polarizations are correlated, even when they are far apart. Measuring the polarization of one immediately determines the polarization of the other, regardless of distance. This phenomenon has been tested extensively. It does not involve signals travelling faster than light. It reflects the fact that the two photons are described by a single quantum state. Their properties are not independent. Entanglement highlights a crucial point. Polarization is not a hidden variable carried by the photon like a tag. It is a property that may not be well defined until measured. Before measurement, the photon can exist in a superposition of polarization states. This superposition is not ignorance. It is not that the photon secretly has a definite polarization, and we just do not know it. Experiments rule out that interpretation. The polarization becomes definite through interaction. This again challenges the idea of substance. Substance implies definite properties independent of observation. Photons do not always have that. Their properties can be context-dependent in a way that classical objects are not. Spin, too, participates in this quantum behaviour. Measurements of photon spin outcomes are probabilistic. The probabilities are fixed by the quantum state, but individual results are not predetermined. This is not due to randomness in the source or noise in the detector. It is inherent. This probabilistic nature does not make photons unreliable. It makes them precise in a different way. The statistics are exact. The unpredictability lies only at the level of individual events. Another subtle point arises when considering reference frames. Polarization is defined relative to a coordinate system. Change the reference frame, and the description of polarization can change. The underlying physics does not. This dependence on description rather than substance reinforces the idea that polarization is relational. Photons do not carry an absolute orientation stamped onto them. Their polarization is meaningful only relative to something else, a detector, a filter, a coordinate system. Without interaction, polarization is a potential, not a fact. Spin and polarization also explain why photons do not clump together. There is no Pauli exclusion principle for photons. Multiple photons can occupy the same state. This is why lasers work. Many photons share the same frequency, polarization, and phase. They behave coherently. This coherence is not due to attraction, it is due to statistics. Photons are bosons. Their spin value places them in a class of particles that prefer to occupy the same state rather than avoid it. Once again, spin classification has consequences without invoking substance. Statistics emerge from symmetry properties, not from material structure. It is worth pausing to consider how far removed this picture is from everyday ideas. Orientation without shape, rotation without mass, angular momentum without spinning parts. All of this feels contradictory only because intuition is trained on macroscopic objects. Photons inhabit a different regime. They are not scaled-down versions of things you can touch. They are governed by rules that do not generalize upward cleanly. Understanding spin and polarization requires letting go of the idea that every property must correspond to a physical part. Instead, properties correspond to allowed behaviors. They describe how something can interact, not what it is made of. This shift is uncomfortable at first, but it is also liberating. It allows physics to describe phenomena that would otherwise remain paradoxical. It allows light to be structured without being solid. As the picture continues to develop, these themes will repeat. Photons will continue to exhibit features that look object-like until examined closely, at which point they resolve into patterns, constraints, and relationships. Spin and polarization are among the clearest examples of this process. They show that the photon is not an empty abstraction, nor is it a tiny object, it is something in between. A quantized excitation with orientation, symmetry and influence, but without mass, without parts, and without substance in the classical sense. One of the most effective ways to understand what something is comes from patiently clarifying what it is not. This is especially true when the thing in question resists ordinary categories, when familiar language keeps pulling the mind toward images that quietly mislead. Photons fall squarely into that territory. Ask what a photon is made of, and the mind immediately begins assembling pictures. Tiny balls, vibrating threads, miniature waves curled up into objects. None of these survive careful examination. To move forward, it becomes necessary to clear the ground, to remove ideas that feel intuitive but do not belong, and to see what remains once those expectations are set aside. The first and most persistent assumption is that a photon must be made of smaller particles. This assumption is deeply ingrained because it has worked so well elsewhere. Atoms were once thought indivisible until they were not. Protons and neutrons were once thought fundamental until quarks entered the picture. It feels natural to assume photons are simply waiting their turn to be revealed as composites of something even smaller. As far as every experiment conducted so far can tell, this is not the case. Photons are elementary. They do not break apart under higher energies. They do not reveal internal structure when probed. No scattering experiment has ever uncovered subcomponents. When photons interact at extremely high energies, they can transform into other particles, but that is not the same as being made of those particles. Transformation is not composition. This distinction matters. A snowflake can melt into water, but it is not made of liquid water as such. A photon converting into an electron-positron pair under the right conditions does not imply that the photon contained those particles inside it all along. It means energy rearranged itself according to allowed rules. Another common idea is that photons are made of energy. This sounds reasonable at first, especially since photons are often described as packets of energy. But energy is not a substance. It is not something that can be isolated, scooped up, or subdivided independently. Energy is a property, a numerical quantity associated with systems and interactions. Saying a photon is made of energy is like saying a moving car is made of speed. Speed describes motion. Energy describes capacity for change. Neither is a material component. Photons carry energy in the sense that they are manifestations of energy transfer, not in the sense that they contain a substance called energy. Closely related to this is the idea that photons are made of light. This sounds circular, but it often hides a deeper confusion. Light, in everyday language, feels like a thing, almost a material. We speak of light filling a room or pouring through a window, but in physics, light is not a substance. It is a process. It is electromagnetic radiation. Saying a photon is made of light is like saying a vibration is made of motion. It restates the phenomenon without explaining it. Another tempting picture imagines photons as extremely small waves, rolled up into compact packages. This hybrid image tries to preserve both wave and particle intuitions at once. While it may feel satisfying, it does not reflect how photons are described mathematically or observed experimentally. A photon is not a wave that has been folded or compressed into a tiny region of space. Its wave-like behavior does not come from physical oscillation of a material medium or object. It comes from the mathematical structure of the electromagnetic field and the rules governing how that field evolves and interacts. When a photon exhibits interference, it is not because it physically spreads itself out like a ripple on water. It is because the probability amplitudes associated with different possible paths combine according to wave equations. The wave description lives in the mathematics of prediction, not in the substance of the photon. Another deeply rooted assumption is that photons must be made of something spatially extended. In everyday experience, things exist in space by occupying regions of it. Even tiny particles are imagined as dots with positions. Photons resist this picture. Photons do not have a well-defined position independent of measurement. You can talk about where a photon is likely to be detected, but you cannot assign it a precise location at every moment without losing information about other properties. This is not a technical limitation. It is a fundamental one. Because of this, photons are not little objects travelling along definite paths the way bullets do. The path language is an approximation that works well at large scales, but it breaks down at the level where quantum effects matter. A photon is not made of spatial extension in the usual sense. There is also a persistent idea that photons might be made of fields themselves, as if the electromagnetic field were a substance, and photons were chunks cut from it. This, too, misleads. The electromagnetic field is not a material medium. It does not consist of smaller bits that can be separated and packaged. It is a fundamental entity described by values assigned to points in spacetime. A photon is an excitation of this field, not a piece of it. The difference is subtle but crucial. An excitation is not a fragment. It is a change in state. When a guitar string vibrates, the vibration is not made of pieces of string breaking off. It is the string behaving differently for a time. Likewise, a photon is the electromagnetic field behaving differently, briefly and locally, within strict constraints. Another mistaken idea is that photons are made of oscillating electric and magnetic fields as physical components. Textbook diagrams often show wavy electric and magnetic field lines oscillating in space, and it is easy to imagine those as physical structures travelling along. Those diagrams are representations, not literal pictures. The electric and magnetic fields associated with a photon are not rigid objects waving back and forth. They are aspects of how the field interacts with charges and currents. The oscillation is a description of change, not a mechanical motion. Photons are also not made of time-varying vibrations in the classical sense. Classical vibrations involve systems that move back and forth through time, passing through states repeatedly. Photons do not experience time internally. Their frequency describes how the field varies relative to observers, not an internal ticking mechanism. Another idea that often appears is that photons might be made of information. This view arises naturally in modern discussions where information plays a central role in physics. Photons certainly carry information, but carrying information is not the same as being made of it. Information requires a physical carrier. It cannot exist independently of physical systems. Photons can encode information in frequency, polarization, and timing, but the information is not the photon's substance. It is a pattern imposed on its properties. Confusing the carrier with the content leads to conceptual errors. Photons are also not made of spacetime curvature. While gravity affects photons, and photons contribute to gravity through their energy, the photon itself is not a fold or wrinkle in spacetime. Gravitational waves are disturbances in spacetime geometry. Photons are disturbances in the electromagnetic field. The two interact, but they are not the same thing. Another persistent misunderstanding is that photons are miniature versions of classical electromagnetic waves. In classical theory, waves can be arbitrarily weak. Their energy can be divided continuously. Photons cannot. The quantum of excitation sets a minimum. You cannot have less than one photon of a given mode. This discreteness does not come from chopping up a wave. It comes from the quantization of the field. The field's allowed excitations are discrete, much like the allowed energy levels of an atom. The photon is one such allowed excitation. There is also a tendency to imagine photons as being made of oscillations in some hidden medium, reviving the old ether idea in modern clothing. This idea persists because waves usually require a medium, but the electromagnetic field does not sit on top of anything else. It is fundamental. No experiment has ever detected a preferred rest frame for light. No medium has been found that light moves through. The field exists in space-time, not in a substance filling space-time. Photons are not ripples in an unseen fluid. Another idea worth dismissing carefully is that photons are made of mathematical abstractions. While photons are described by mathematics, they are not merely mathematical. Mathematics is the language used to describe their behaviour, not their substance. Photons have observable effects independent of human description. The danger here is swinging too far in the opposite direction, treating photons as unreal because they are abstract. But abstraction does not imply non-existence. Gravity is abstract, fields are abstract, laws are abstract, their effects are not. Photons are also not made of probability. Probability describes outcomes. It is not a physical ingredient. The probabilistic nature of photon behavior reflects the structure of quantum theory, not the composition of photons themselves. A photon is not a tiny clock, not a spinning bead, not a vibrating pellet, not a wave rolled into a ball, not a piece of substance carved from a field, not stored energy, not information incarnate, not a geometric feature of space-time. Each of these ideas captures something about photons while missing the deeper point. Removing these misconceptions leaves a quieter but more accurate picture. A photon is a quantized excitation of the electromagnetic field. That sentence sounds abstract because it is abstract. But abstraction here is precision, not evasion. Quantized means that the excitation comes in discrete units. Excitation means a change in state, not a piece of material. Electromagnetic field means a fundamental entity that governs electric and magnetic interactions. This description does not tell you what photons are made of because that question no longer applies cleanly. Photons are not assembled. They are allowed events. This can feel unsatisfying if one expects reality to be built from smaller and smaller bits of stuff. But modern physics suggests that the deepest level is built from rules, symmetries, and fields, not from tiny objects in the classical sense. Photons are among the clearest examples of this shift. They show that something can be real, influential, and essential without being made of matter. They challenge the intuition that substance is the foundation of existence. Understanding what photons are not made of helps prevent future confusion. It prevents the mind from reaching for metaphors that fail quietly. It clears space for a more accurate, if less picturable, understanding. As the exploration continues, this cleared ground becomes important. When discussing fields, excitations, and empty space, the temptation to reintroduce substance-based thinking will return. Recognizing it early makes it easier to resist. Photons are not missing substance. They do not lack something we simply have not discovered yet. Their nature reflects a different organizational principle. They are not built from pieces. They are expressions of how the universe allows energy and information to move. Imagine the universe as a vast interconnected web, not made of objects or particles but woven from invisible fields that stretch out into every corner of existence. These fields are not things you can touch or see in the traditional sense, but they are just as real as anything else in physics. The electromagnetic field is one such entity. It exists everywhere, even in what we might call empty space. The word empty is misleading though, because space is never truly empty. It is filled with fields, and within those fields particles like photons emerge as quantized excitations. Understanding how this works requires stepping away from the classical idea of things as tangible, isolated objects and embracing a new, deeper perspective. The electromagnetic field is one of the fundamental fields of nature. It permeates all of space, connecting everything, even if we don't see or feel its presence directly. It is the field that governs electric and magnetic forces. The electric and magnetic components of this field are not separate entities. They are two intertwined aspects of the same underlying reality. The field can be thought of as a backdrop against which electric charges and currents move, creating forces that we observe as electricity and magnetism. In this sense, empty space is not empty at all. It is a dynamic, vibrating sea of electromagnetic field potential. Even when there are no charges or currents present, this field still exists, and its effects can still be felt. What we think of as nothing is actually a sea of energy waiting to be excited into action. Now, let's pause here to consider a key point. A field is not an object, nor is it something made of parts. A field is a property of space itself, defined by the values it assigns to every point in space and time. Imagine the field as a vast invisible ocean that stretches throughout the universe. The field doesn't have a specific location. It is everywhere. But it is not a fluid substance like water. It doesn't slosh around or get pushed by winds. It is more abstract than that, a continuous mathematical entity that fills all of space. This is a difficult concept to grasp because we're used to thinking of space as a void that can be filled with things, matter, energy, or objects. But here, space itself is not empty. It is a framework, a stage upon which all the drama of the universe unfolds, and that drama is provided by fields. These fields do not sit still, they are dynamic. The electromagnetic field is constantly in motion, even in the absence of light. When charged particles move, they disturb the field, sending ripples through it. These disturbances are what we experience as electromagnetic waves, light, radio waves, X-rays, and so on. At the most fundamental level, the electromagnetic field is not a thing you can hold or touch. It is a mathematical description of how electric and magnetic forces interact. The field tells you the force that would be felt by a charge at any given point in space. But this description is not limited to charges. The field can exist and vibrate in the absence of charges, just as the surface of a pond can ripple without a rock being thrown in. This brings us to the idea of excitations. A field, while it can be thought of as continuous and omnipresent, can also be excited. When a field vibrates, it is disturbed from its equilibrium state. These disturbances are what we call excitations of the field. In the case of the electromagnetic field, these excitations are photons. When the electromagnetic field is disturbed in a particular way, a photon is created. It is not a piece of the field, not a part of it, but an excitation, a quantum of energy and momentum travelling through the field. It's crucial to understand that the photon itself is not a chunk of electromagnetic field that can be split into pieces. The photon is an indivisible excitation, a brief, localized ripple in the electromagnetic field that travels through space. These excitations are quantized, meaning they come in discrete amounts. You can have 1 photon, 2 photons, and so on, but not half a photon. The photon is not made of the field in a physical sense. It is the field behaving in a very particular way, and that behavior can be described as a photon. This concept of excitations leads to a profound shift in how we think about particles and forces. In classical physics, forces are transmitted by particles, gravitational forces by gravitons, electromagnetic forces by photons, and so on. But in quantum field theory, particles like photons are not separate objects that move through space. They are the field itself, briefly excited in a particular way. A photon is not a bullet travelling through space. It is the electromagnetic field temporarily shifting, carrying energy and momentum across space. This brings us to the final piece of the puzzle, the nature of empty space. In classical physics, empty space was thought to be a true void, a place where nothing existed. However, quantum field theory radically changes this idea. Space is never truly empty. Even in a vacuum, space is filled with fields that have values at every point. These fields are not static. They're constantly fluctuating, even when nothing is happening. This is known as the vacuum state or vacuum fluctuations. These fluctuations are responsible for the creation of virtual particles. These particles are not real in the traditional sense. They exist for a fleeting moment before they vanish, and their existence cannot be directly observed. But their effects can be. For example, virtual particles are involved in the Casimir effect, where 2 uncharged metal plates placed in a vacuum experience a small attractive force due to the fluctuations of the electromagnetic field between them. The idea of vacuum fluctuations helps explain how particles like photons can appear and disappear. They are not permanent residents of space. They emerge from and return to the field, appearing as excitations of the electromagnetic field. This process is governed by the uncertainty principle, which tells us that there is always some degree of fluctuation in the energy of the field, even in the absence of observable particles. These fluctuations are what give rise to the creation and annihilation of particles like photons. In this sense, empty space is not truly empty. It is filled with potential. It is a medium in which fields vibrate and fluctuate, and those vibrations are what give rise to particles. Space itself is the stage upon which everything else unfolds. Without the field, there would be no photons, no light, no electromagnetic radiation. The field is not just a backdrop. It is the essential fabric of reality, and photons are the excitations that emerge from it. What we think of as empty space is a rich and dynamic environment, filled with potential for the creation of photons and other particles. These excitations are not the field itself, but its behaviour, its temporary disturbance. They travel through space carrying energy and momentum and interact with matter in a way that we can measure. But the field remains the medium in which these excitations occur, and it is this underlying field that forms the true substance of the universe, not the particles that appear within it. This understanding of fields, excitations, and empty space shifts the focus away from the traditional idea of material substance. Instead of imagining the universe as being made of solid objects or particles that can be divided into smaller pieces, we see it as being made of dynamic fields that interact and excite each other. The particles we observe, like photons, are not fundamental in the way we think of material objects. They are excitations of these fields, momentary disturbances that travel through space. This change in perspective opens up new avenues of thought. It challenges our intuition and forces us to abandon the idea that everything must be made of matter. Fields are the true substance of the universe, and particles like photons are simply localized excitations of these fields. They are not objects in the traditional sense, but manifestations of the underlying dynamics that govern how energy and information move through space. Photons do not originate in empty space without cause. Every photon that exists has a history tied to matter, to energy rearranging itself under strict rules. Nowhere is this more evident than inside atoms and stars, where photons are constantly being created, absorbed, delayed, scattered, and transformed. These environments reveal something crucial about photons. They are not free-floating curiosities that occasionally interact with matter. They are woven into the very processes that allow matter to exist, persist, and change. Inside an atom, photons appear at moments of transition. Atoms are not miniature solar systems with electrons orbiting smoothly around a nucleus. They are quantum systems with allowed energy states. An electron bound to an atom can only occupy certain energy levels, not arbitrary ones. These levels are determined by the structure of the electromagnetic field and the rules of quantum mechanics. When an electron changes from one allowed state to another, energy must be conserved. That energy difference does not vanish. It appears as a photon. This process is precise. If an electron drops from a higher energy state to a lower one, the photon emitted has an energy exactly equal to the difference between those states. No more, no less. There is no flexibility. The frequency of the photon is fixed by that energy gap. This is why atomic emission spectra consist of sharp lines rather than continuous bands. Each line corresponds to a specific transition. This precision tells us something important about photons. Their properties are not arbitrary. They are constrained by the systems that produce them. A photon emitted by a hydrogen atom carries a frequency that reflects hydrogen's internal structure. That frequency is a message encoded by the atom, and the photon carries it outward unchanged until interaction. Absorption is the reverse process. When a photon encounters an atom, it may be absorbed if its energy matches an allowed transition. The photon does not gradually give up energy. It is either absorbed entirely or not at all. Partial absorption does not occur. If the energy matches, the electron jumps to a higher energy state, and the photon ceases to exist as an independent excitation. This all-or-nothing behaviour is one of the clearest demonstrations that photons are not divisible objects. They are not packets that can be shaved down or partially consumed. They are indivisible events. Inside atoms, photons therefore act as precise accounting tools. They ensure that energy changes happen in discrete steps. Without photons, atoms could not radiate energy in a controlled way. They could not cool, glow, or respond selectively to electromagnetic radiation. The same principles apply on a vastly larger scale inside stars. A star is not a static object. It is a continuous process, a balance between gravity pulling inward and energy pushing outward. That outward push is provided largely by photons. In the core of a star, nuclear fusion releases enormous amounts of energy. Protons combine to form heavier nuclei, and a small amount of mass is converted into energy. That energy does not escape immediately. The interior of a star is dense. Photons produced in the core do not travel freely to the surface. Instead, they embark on a long, indirect journey. A photon created in the sun's core may take tens of thousands of years to reach the surface. This seems surprising given that photons move at the speed of light. The delay is not due to slow motion, it is due to repeated interactions. The photon is absorbed by charged particles, re-emitted, scattered, absorbed again, and so on. Each interaction resets the photon's identity. The original photon does not survive the journey. Energy does, but photons do not persist as individuals. This is a critical point. Photons inside stars are constantly being destroyed and recreated. The energy moves outward through a random walk of interactions. The photons that finally escape the surface of the sun are not the same photons created in the core. They are newly created excitations carrying energy that has been redistributed many times. This process underscores a theme that has appeared repeatedly. Photons are not enduring objects. They are transient carriers of energy. They appear where energy is released and disappear where energy is absorbed. Once photons reach the surface of a star and escape into space, their behavior changes dramatically. Space is sparse. Interactions become rare. A photon leaving the sun's surface can travel for 8 minutes without interruption before reaching Earth. During that time, its frequency remains fixed. Its polarization remains fixed unless altered by interaction. It carries information about the conditions at the surface where it was created. This is how stars communicate their properties across space. By analyzing the light from stars, scientists can determine their composition, temperature, motion, and magnetic fields. All of this information is encoded in the photon's frequencies, intensities, and polarizations. Inside atoms and stars, photons also play a role in equilibrium. Matter and radiation exchange energy continuously. In thermal equilibrium, the rate of photon emission equals the rate of photon absorption at each frequency. This balance determines the spectrum of radiation emitted by a body at a given temperature. The concept of blackbody radiation arises here. A blackbody is an idealized object that absorbs all radiation incident upon it and emits radiation according to its temperature. The spectrum of blackbody radiation is determined by the statistical distribution of photon energies. This distribution played a crucial role in the development of quantum theory because classical physics could not explain it. Inside stars, the radiation field approaches a blackbody distribution in regions of high density. Photons are constantly interacting with matter, exchanging energy, and reaching statistical equilibrium. The resulting spectrum reflects the temperature of the region. This again emphasizes that photons inside matter are not free agents. They are tightly coupled to their environment. Their properties reflect the conditions under which they are created and destroyed. Another important role photons play inside atoms and stars is in pressure. Radiation pressure is not negligible in stellar interiors. Photons carry momentum. When they are absorbed or scattered, that momentum is transferred to matter. In massive stars, radiation pressure can be strong enough to counteract gravity significantly. In the most massive stars, radiation pressure can even dominate. It limits how massive a star can become. If a star becomes too luminous, the outward push of photons can overcome gravity, driving material away in powerful stellar winds Here again, photons influence matter without having mass. They exert force through momentum transfer, not through weight. Inside stars, this effect is cumulative and decisive. Photons also mediate energy transport in different ways depending on the star's structure. In some regions, energy is transported primarily by radiation. In others, convection dominates. The balance between these mechanisms depends on opacity, which is a measure of how easily photons interact with matter. Opacity depends on atomic structure. Different elements absorb and scatter photons differently. This affects how energy flows outward and shapes the star's evolution. The life cycle of a star is therefore intimately tied to how photons interact with atoms under extreme conditions. Inside atoms, photons also influence stability. Atoms are stable because electrons occupy allowed states. If electrons could radiate continuously like classical charges, atoms would collapse. The quantization of energy levels and the discrete emission of photons prevent this collapse. This stability is not an accident. It arises from the same rules that govern photon behavior. The electromagnetic field supports only certain excitations. Atoms can only exchange energy in discrete amounts. Photons enforce this discreteness. The same principles apply in more exotic environments. In dense stellar remnants like white dwarfs and neutron stars, photons interact with matter under extreme conditions. In neutron stars, matter is so dense that photons struggle to escape. The surface layers emit radiation shaped by intense gravitational and magnetic fields. In these environments, photon behavior reveals new aspects of fundamental physics. Polarization patterns can indicate magnetic field strengths billions of times stronger than any produced on Earth. Gravitational redshift alters photon frequencies as they climb out of deep gravitational wells. Yet even here, photons remain faithful messengers. They obey the same rules everywhere. They carry energy, momentum, and information according to the same constraints, regardless of environment. Another important aspect of photons inside atoms and stars is that they participate in feedback loops. Energy emission affects temperature. Temperature affects emission rates. These feedbacks regulate stellar behavior. Without photons, stars could not self-regulate. Photons also play a role in chemical processes beyond stars. In interstellar space, photons drive chemical reactions by breaking molecular bonds. Ultraviolet photons from stars shape the chemistry of galaxies. They determine where molecules can form and survive. This again highlights that photons are not passive. They actively shape the structure and evolution of matter across cosmic scales. Despite this influence, photons themselves remain ephemeral. They do not accumulate inside atoms. They do not pile up inside stars indefinitely. They are constantly created and destroyed. Matter persists. Photons pass through. This asymmetry is important. Matter stores energy. Photons transport it. Matter has identity. Photons do not. Inside atoms and stars, this division of roles becomes unmistakable. Understanding photons in these environments also clarifies why asking what a photon is made of can be misleading. Inside atoms, photons are not assembled, they are released. Inside stars, photons are not objects travelling intact from core to surface. They are processes repeated countless times. The photon is not a building block in the way atoms are building blocks. It is a mediator. It is how energy moves between configurations of matter. This mediator role explains why photons are everywhere in energetic environments. Wherever energy is changing form, photons are involved. Wherever matter rearranges itself, photons appear or disappear. Inside atoms and stars, photons reveal their true nature most clearly. They are not tiny things bouncing around. They are quantized interactions, allowed transitions and field excitations that enforce the rules of energy conservation. As this picture settles in, it becomes easier to see why photons behave the way they do in empty space as well. The behavior in vacuum is not separate from their behavior in matter. It is the same rules applied under different conditions. The photons that reach your eyes from a star began as part of a complex dance of interactions deep inside that star. They are the final links in a long chain of energy transfer. They carry with them the imprint of atomic transitions, thermal distributions, gravitational fields, and magnetic environments. And yet, by the time they arrive, they are simple again. They have frequency, polarization, direction, nothing more, no memory of the path taken, no record of intermediate steps. This simplicity is not ignorance, it is efficiency. It allows photons to function as universal messengers. Light has always been associated with knowledge. Long before physics formalized the concept, language had already done so. To illuminate is to explain. To shed light is to make something known. Darkness is ignorance. Light is understanding. These metaphors feel natural because, in a very literal sense, light is how information reaches us. Almost everything you know about the world beyond your own body has arrived via photons. And yet, the deeper physics looks, the clearer it becomes that light does not merely deliver information, it also defines its limits. To understand this, it helps to begin with a simple but often overlooked fact. Information is not abstract in the physical world. It must be carried by something. A message written on paper requires ink and matter. A sound requires vibrating air. A digital signal requires electrons moving through circuits. In every case, information is tied to a physical process. Light is one of the most efficient carriers of information the universe has, but it is still bound by physical rules. When a photon travels from one place to another, it carries information in several ways at once. Its frequency encodes energy. Its direction encodes spatial relationships. Its polarization encodes orientation. Its timing encodes sequence. None of this information is symbolic. There is no codebook hidden inside the photon. The information exists because physical systems respond differently to different photon properties. When your eye receives light, it does not decode a message in the way a computer decodes data. Instead, photons interact with molecules in your retina. Those interactions trigger chemical changes. Those changes propagate through neurons. Meaning is constructed downstream, in the brain. The photon itself carries no awareness of what it signifies. It carries only physical constraints. This distinction matters because it shows that information is relational. It exists at the intersection of a carrier and a receiver. A photon's frequency only becomes colour when a visual system interprets it. Its polarization only becomes a bit value when a detector is set up to distinguish polarizations. Information is not a substance moving through space. It is a pattern of possible interactions. Because photons are so well behaved, so consistent, they are ideal for transmitting these patterns. A photon's frequency does not drift in empty space. Its polarization remains fixed unless something changes it. Its speed is constant. These properties make light reliable. They allow distant events to be correlated with local measurements. Astronomy is the clearest example. Every image of a distant galaxy is an information transfer problem. Photons leave stars and gas clouds, travel across expanding space for millions or billions of years, and are absorbed by detectors on Earth. From those interactions alone, scientists infer composition, motion, temperature, age, and structure. No other physical messenger could do this so effectively. And yet, even here, limits appear. The information carried by light is not unlimited. Photons cannot tell you everything about their origin. They do not carry full histories. They carry only what survives interaction. For example, when light scatters off matter, some information is lost. Direction changes. Phase relationships are scrambled. The photon still exists, but its ability to convey precise origin details diminishes. This is not a technological limitation. It is a physical one. Interaction trades information for change. Absorption ends information transfer entirely. Once a photon is absorbed, it no longer exists as a carrier. Its energy and momentum are transferred, but the structured pattern that defined it is gone. Information carried by that photon does not persist unless it is recorded elsewhere. This impermanence leads directly to limits of knowing. If information is carried by photons and photons are destroyed upon measurement, then measurement itself has a cost. You cannot extract information without altering the system. This is not philosophical caution, it is a physical rule. Quantum mechanics makes this explicit. Measuring a system requires interaction. Interaction involves exchange of energy and momentum. Photons are often the mediators of that exchange. When you observe an object, photons scatter off it and enter your eyes or instruments. Those photons carry information, but in doing so, they disturb the object. At everyday scales, this disturbance is negligible. At atomic scales, it is not. Trying to see an electron requires photons with short wavelengths, which means high energy. Those photons significantly disturb the electron state. Precision in position comes at the cost of precision in momentum. This is not a limitation of microscopes. It is built into the structure of light itself. The Heisenberg uncertainty principle is often misunderstood as a statement about human ignorance. It is not. It is a statement about the limits imposed by the carriers of information. Photons cannot probe arbitrarily small distances without carrying large energies. Those energies change what is being measured. The limits of knowing are enforced by the properties of light. This becomes even clearer when considering time. Measuring rapid changes requires high-frequency photons. Those photons carry large energy. Probing short timescales inevitably injects energy into the system. The act of observation becomes an intervention. Even in classical contexts, light sets limits. The finite speed of light means that information cannot be instantaneous. When you see a star, you see it as it was, not as it is. When you look across a room, there is a tiny delay. These delays are negligible in daily life, but fundamental in principle. There is no universal now carried by light. Information arrives at finite speed. This finite speed also limits causality. No information can travel faster than light. This is not a rule imposed on light. It is a rule revealed by light. Photons define the maximum speed at which influence can propagate. This defines the structure of spacetime itself. Because of this, there are regions of the universe from which light has not yet reached us and never will. Information from beyond the observable universe is inaccessible in principle, not just in practice. No improvement in technology can change this. The limit is set by expansion and the speed of light. Even within the observable universe, information degrades with distance. Interstellar dust absorbs and scatters photons. Cosmic microwave background radiation carries information from the early universe, but it has been stretched, cooled, and blurred by expansion. What remains is remarkable, but incomplete. This degradation is not accidental. It reflects the second law of thermodynamics. Information disperses. Order spreads into disorder. Photons participate in this process. While individual photons preserve frequency and polarization in vacuum, ensembles of photons tend towards statistical distributions. Fine details wash out. This brings us to entropy. Information and entropy are closely related. Systems with high entropy have less accessible information about their microscopic states. Light interacts with entropy in complex ways. Emission of light can increase entropy by spreading energy. Absorption can decrease local entropy but increase it elsewhere. Stars, for example, are low-entropy structures that radiate energy as photons. That radiation increases the entropy of the surrounding universe. The photons carry energy outward, allowing complex structures to exist temporarily. Information flows, but at a thermodynamic cost. At the quantum level, light also imposes limits through complementarity. Certain properties cannot be known simultaneously with arbitrary precision. Frequency and timing are one example. Polarization components are another. Choosing how to measure a photon determines which information becomes available and which becomes inaccessible. This is not because the photon is hiding information. It is because information is not simultaneously real in all forms. Measurement defines which aspects become concrete. The photon does not carry a full list of properties waiting to be revealed. Some properties are mutually exclusive in how they can be accessed. Entanglement adds another layer. Entangled photons can share information in ways that defy classical intuition. Measuring one affects the description of the other. This does not transmit usable information faster than light, but it does reveal that information is not always localized. In entangled systems, information about the whole exists without being stored entirely in the parts. Photons can participate in these systems, carrying correlations rather than independent messages. This challenges the idea that information is something each photon possesses individually. Even so, entanglement does not remove limits. You cannot use entangled photons to send messages instantaneously. The statistical outcomes obey the same constraints as all other photon interactions. Light remains the boundary. At this point, it becomes clear that light does not simply enable knowing. It structures knowing. It determines what can be known, how precisely, and at what cost. The properties of photons are not neutral carriers. They shape the epistemology of the universe. This is why different kinds of light reveal different kinds of information. Radio waves probe large-scale structures. Infrared reveals heat. Visible light reveals surfaces. X-rays reveal dense interiors. Gamma rays reveal extreme processes. Each band carries information tied to its frequency and energy. No single kind of light tells the whole story. It is also why some information is forever inaccessible. Processes that do not emit photons cannot be observed electromagnetically. Dark matter, if it does not interact with light, cannot be seen directly. Its existence is inferred indirectly through gravitational effects. The absence of photons is itself a limit on information. Even where photons are present, not all information survives propagation. Phase information can decohere. Polarization can randomize. Frequency can shift due to motional gravity. What reaches a detector is always a filtered version of what was emitted. This filtering is not malicious. It is structural. It arises from the same rules that make photons reliable carriers in the first place. The universe does not conspire to hide information. It simply operates under constraints. Recognizing these constraints changes how knowledge is framed. Science is not about uncovering absolute truths hidden behind appearances. It is about extracting reliable patterns from limited signals. Photons are the primary signals. Their limitations are the boundaries within which understanding operates. This does not diminish the achievement of knowledge, it clarifies it. Knowing becomes an exercise in respecting constraints, not overcoming them. Light, then, is both generous and strict. It delivers information across vast distances with remarkable fidelity. It also enforces limits that cannot be bypassed. It allows us to see stars and atoms, but not everything about them. It lets us measure, but not without disturbance. It enables communication, but not instantaneity. Photons are not just messengers of knowledge, they are gatekeepers. They define the terms under which reality can be accessed. As this understanding settles, it naturally leads to deeper questions. If photons shape what can be known, what does that imply about time, experience, and observation itself? If a photon does not experience time, but structures how time is measured, what role does it play in the flow of events? Time feels unavoidable. It presses forward whether we pay attention to it or not. It marks change, aging, sequence, before and after. Every experience you have ever had is threaded together by time's passage. And yet, photons sit strangely outside this familiar structure. According to our best physical theories, photons do not experience time at all. This statement is not metaphorical, and it is not philosophical decoration. It follows directly from the way space, time, and motion are woven together in modern physics. Understanding why photons never experience time forces us to re-examine what time actually is, how it relates to motion, and why intuition breaks down at the most fundamental level. To begin, it is important to clarify what experiencing time means in physics. Experience in the human sense involves consciousness, memory, and awareness, none of which apply to photons. Physics uses a more precise concept called proper time. Proper time is the time measured by a clock moving along with an object. For you, proper time corresponds closely to the time you feel passing. Your heart beats, your cells change, your clock ticks. All of that happens along your path through space-time. For objects with mass, proper time always flows. Even if you move very fast, time still passes for you, though it may pass more slowly relative to someone else. This slowing of time with speed is time dilation, a well-tested consequence of special relativity. As an object's speed increases, its proper time runs more slowly compared to a stationary observer. This effect is not psychological, it is physical. Clocks on fast-moving airplanes tick slightly more slowly than clocks on the ground. Particles moving near the speed of light live longer than identical particles at rest. Time itself behaves differently depending on motion. As speed increases, time dilation becomes more pronounced. At everyday speeds, the effect is negligible. At relativistic speeds, it becomes dramatic. The closer an object's speed gets to the speed of light, the more its proper time slows relative to the rest of the universe. Now comes the crucial point. Photons move at the speed of light. Not approximately, not usually, always. There is no frame of reference in which a photon is at rest. You cannot ride alongside a photon. There is no valid inertial frame where the photon's speed is zero. When the equations of relativity are extended to this limit, something remarkable happens. The proper time along a photon's path becomes zero. From emission to absorption, no time elapses in the photon's own frame. The interval of proper time is exactly null. This does not mean that photons are frozen or timeless in a mystical sense. It means that the concept of proper time simply does not apply to them the way it applies to massive objects. The space-time interval along a photon's trajectory is different in kind from that of objects with mass. In relativity, space-time intervals come in three types: time-like, space-like, and light-like. Time-like intervals correspond to paths objects with mass can take. Space-like intervals correspond to separations that cannot be connected by any signal travelling at or below the speed of light. Light-like intervals are exactly those followed by photons. Along a light-like path, the space-time interval is zero. This is not an approximation. It is a defining feature. Because proper time is derived from the space-time interval, a zero interval means zero proper time. This result is deeply counterintuitive because it clashes with everyday ideas about motion and duration. A photon emitted by a star a billion light-years away takes a billion years to reach Earth, as measured by clocks on the star and on Earth. Yet along the photon's own path, no time passes at all. This is not a contradiction. It reflects the relativity of time itself. Time is not an absolute background against which events unfold. It is part of the structure of space-time intertwined with motion. To see why this matters, consider what it means for an object to experience time. Experience requires change. Change requires internal states that evolve. Clocks tick because something inside them moves or oscillates. Living organisms age because biochemical processes unfold. A photon has no internal structure that can change independently of its motion. It has no rest frame, no internal clock, no sequence of internal states. Its defining properties, frequency and polarization, are not internal processes unfolding over time. They are relational properties defined with respect to observers and interactions. Frequency, for example, does not represent an internal oscillation experienced by the photon. It represents how the electromagnetic field varies in time as measured by an observer. The photon itself does not feel these oscillations. There is no internal rhythm counting cycles. This distinction is subtle but essential. It prevents the mind from imagining photons as tiny ticking entities racing through space. They are not clocks, they are links between events. Another way to approach this is through causality. For objects with mass, there is a sequence of events along their world line. One event causes the next. Memory and causation require temporal ordering. For photons, emission and absorption are the only meaningful events. There is no chain of intermediate events in the photon's own frame. From the perspective of the photon's path, emission and absorption are coincident. They are the same event in terms of proper time. The photon does not traverse a history, it connects two events directly. This idea helps explain why photons are such effective messengers. They do not degrade with age because they do not age. They do not experience wear, fatigue, or decay. Their properties remain fixed not because they are protected, but because there is no internal time along which change could occur. It also explains why photons do not experience processes like entropy increase. Entropy is a measure of how many internal configurations a system can have. Systems evolve towards states with higher entropy over time. A photon has no internal degrees of freedom that can rearrange. There is no entropy associated with a single photon's internal state evolving through time. Entropy applies to ensembles of photons, to radiation fields as a whole, not to individual photons as entities moving along a path. This absence of time experience also clarifies why photons cannot be said to witness the universe. They do not observe events along the way, they do not pass through intermediate stages, they do not accumulate information, they simply connect emission and absorption. From the standpoint of relativity, this is not optional. Allowing photons to experience time would require a rest frame for light, which would break the structure of spacetime. The constancy of the speed of light and the absence of a photon rest frame are foundational. It is sometimes tempting to imagine what the universe looks like from the photon's point of view. Physics strongly discourages this phrasing. There is no valid inertial frame in which a photon is at rest, so there is no consistent way to define a photon's viewpoint. Any attempt to do so leads to mathematical contradictions. This is why physicists say photons do not experience time, rather than saying they experience time differently. There is no alternative rate of time flow for photons. There is none at all. This fact also sheds light on why photons can connect distant regions of the universe so cleanly. From the photon's path, there is no separation in time. Distance and duration are observer-dependent concepts. Along a light-like path, the distinction collapses. This collapse does not imply that space itself disappears. Spatial separation is still meaningful to observers with mass. But for the photon's trajectory, space and time are arranged such that the path is null. It does not accumulate interval. Understanding this requires letting go of the idea that time is something everything must participate in equally. Time is not a universal substance flowing everywhere at the same rate. It is a relational quantity tied to motion and mass. Mass is the key difference. Objects with mass cannot reach the speed of light. They always move more slowly, and therefore always experience time. The presence of mass guarantees a time-like path through space-time. Photons, being massless, are not bound by this constraint. Their masslessness is not merely a missing property. It is what places them on light-like paths. It is what removes proper time from their description. This connects back to earlier discussions about substance. Mass is often taken as evidence of substance. Photons lack mass, and they also lack time experience. These absences are not coincidental. They are connected. Substance, persistence, and time experience go together. Photons have none of these in the classical sense. They are transient excitations, not enduring entities. Another consequence of photons not experiencing time is that they cannot carry memories. Memory requires a sequence of states, with later states encoding information about earlier ones. Photons do not have later and earlier states internally. They cannot remember where they have been. This is why photons do not accumulate damage or history. A photon passing near a star does not carry a mark of that encounter, unless its properties are altered by interaction. There is no internal ledger recording near misses or long journeys. This also explains why photons cannot decay. Many particles decay because they have internal structures that can rearrange into lower energy configurations over time. Photons have no such structure. There is nothing inside them that can evolve toward decay. Photons can be absorbed, but that is not decay. It is interaction. The photon ceases to exist because its energy is transferred, not because it internally transformed. The absence of time experience also clarifies why frequency should not be interpreted as an internal clock. It is tempting to think of a photon as oscillating billions of times per second, counting cycles as it travels. This picture is misleading. The oscillation described by frequency belongs to the electromagnetic field as measured by an observer. It is not an internal process unfolding for the photon. There is no ticking experienced along the photon's path. This distinction becomes especially important when considering relativistic effects like time dilation and Doppler shift. When a photon's frequency changes due to relative motion or gravity, it is not because the photon's internal clock slowed down or sped up. It is because different observers slice spacetime differently. Frequency is observer-dependent. Proper time for massive objects is not. For photons, there is no proper time to begin with. At this point, it becomes clear why photons sit at the boundary between space and time. They define the structure of spacetime without participating in it the way massive objects do. They set the maximum speed. They define causal cones. They connect events without inhabiting the interval between them. This makes photons unique. No other entities in physics behave this way. Even other massless fields like gravitational waves follow similar light-like paths, but photons are the most familiar example. Understanding why photons never experience time also sheds light on why they are so central to physics. They are not just messengers within spacetime, they help define spacetime itself. The geometry of spacetime is such that light-like paths exist. The laws of physics are invariant under transformations that preserve the speed of light. Time and space adjust to accommodate light's behavior, not the other way around. This reverses the intuitive picture. Light does not move through space and time as they exist independently. Space and time are structured in a way that allows light to behave as it does. Once this is understood, the statement that photons never experience time stops sounding mysterious and starts sounding inevitable. Given masslessness, given the structure of space-time, given the invariance of the speed of light, there is no other possibility. This understanding does not make photons alien or detached from the universe. It makes them deeply integrated. They are the threads that stitch together events across space-time. Darkness is often treated as an absence, a lack, a failure of something to be present. When the lights go out, when the sun sets, when vision softens and detail fades, it can feel as though something has been taken away. And yet, from the perspective we've been building, darkness is not a void left behind by departing photons. It is simply a condition in which fewer interactions are happening, fewer exchanges, fewer messages in motion. Returning gently to the dark, then, is not about reaching an end. It is about easing back into a state where activity slows, where the constant traffic of light thins out, and where the universe becomes quieter without becoming empty. Every photon we have talked about exists only briefly, even if that briefness stretches across billions of years for observers like us. Photons are born in transitions and vanish in interactions. They do not linger. They do not accumulate experiences. They do not remember the paths they have taken. And because of this, the universe is never crowded with old light in the way a room fills with dust. Light is always in motion, or being absorbed, always passing through or ending somewhere. Darkness in this sense is not the absence of photons entirely. It is the absence of enough photons to trigger noticeable interactions. Even the deepest interstellar space is filled with radiation. The cosmic microwave background surrounds everything, a faint afterglow of the early universe, Radio waves pass through you constantly. Infrared photons emitted by warm objects drift in all directions. Darkness is relative, contextual, dependent on sensitivity. This reframing matters because it dissolves a common intuition. We tend to imagine darkness as nothingness and light as somethingness. But throughout this exploration, light has turned out not to be a substance at all. Photons are not pieces of matter filling space. They are events. They are interactions in transit. When those events become rare, we call the result dark. Returning to the dark, then, is returning to a state where fewer interactions demand attention, where information flow slows, where the electromagnetic field remains present but largely unexcited. Nothing fundamental disappears. The rules remain. The fields remain. The potential remains. This is why darkness can feel calming. Fewer photons reaching your eyes means fewer signals to process. Your brain, which evolved to respond to changes carried by light, finds less to do. Vision softens. The world becomes less detailed, less demanding. Attention naturally turns inward or relaxes outward without urgency. From the universe's perspective, darkness is not unusual. Most of space is dark most of the time. Stars are sparse. Galaxies are separated by enormous distances. Bright regions are exceptions, islands of intense activity surrounded by vast quiet. And yet, even in those quiet regions, the same rules apply. The electromagnetic field is still there. It still allows excitations. Photons can still be created if conditions arise. Darkness is not a shutdown. It is a low-activity state. This perspective helps resolve a subtle tension that can arise when thinking about photons. If photons are so central, so essential, so deeply woven into the structure of reality, why is there darkness at all? The answer is that photons are not omnipresent objects. They are contingent events. They appear when energy rearranges itself in particular ways. When those rearrangements slow or become rare, photons become rare as well. Stars shine because nuclear reactions produce energy gradients that must be released. Atoms glow because electrons change states. Fire emits light because chemical bonds rearrange energetically. When these processes are absent or balanced, light emission decreases. Darkness follows naturally. In that sense, darkness is a sign of equilibrium. A system that is no longer rapidly changing has little reason to emit photons. Energy flows become minimal. Gradients flatten. The need for messengers diminishes. This is not stagnation. It is stability. Throughout this discussion, photons have appeared again and again as messengers, mediators, and connectors. They move energy, momentum, and information. They enforce limits. They reveal structure. But they do not stay. They do not settle. They do not form the background. They pass through it. The background, the constant presence, is the field itself. The electromagnetic field does not turn off when photons are absent. It does not require excitation to exist. Darkness is not the absence of the field. It is the field in a low excitation state. This distinction becomes especially important when considering the early universe. In its earliest moments, the universe was opaque. Photons were constantly interacting with matter. Light could not travel freely. There was no darkness in the sense we experience it. Only later, when the universe expanded and cooled enough for atoms to form, did photons begin to move freely. Darkness emerged as space grew larger than sources of light. Darkness, then, is a product of scale. It appears when distances between emitters grow large compared to the reach of their photons. It appears when time stretches between emission events. It appears when interactions become sparse. Returning gently to the dark can therefore be understood as returning to the dominant state of the universe. Brightness is local and temporary. Darkness is widespread and enduring. This does not diminish light's importance. It contextualizes it. Light is how change announces itself. Darkness is how stability rests. At a more personal level, this perspective mirrors daily experience. Activity peaks and fades. Stimuli arrive and recede. Periods of engagement alternate with periods of rest. The nervous system is not designed to process constant brightness indefinitely. It needs darkness to reset sensitivity, to recalibrate, to prepare for future signals. Photons play a role even here. The absence of light affects hormone production. It shifts circadian rhythms. It alters perception. Darkness is not neutral. It actively shapes biological processes by changing photon availability. Yet again, this is not because darkness is something imposed. It is because photons are absent as triggers. The body responds to fewer interactions by changing state. Returning gently to the dark, then, is not about ending the story of photons. It is about recognizing where their role naturally pauses. The field remains. The potential remains. The rules remain. Only the activity changes. One of the quieter insights that emerges from everything discussed is that photons are never the foundation. They are always the intermediaries. They connect, but they are not what is being connected. They carry, but they are not what is being carried. Atoms persist when photons are absent. Fields persist when photons are absent. Spacetime persists when photons are absent. Darkness does not erase structure. It reveals how much structure does not depend on active exchange. This is why the question, what is a photon made of, eventually dissolves into a different understanding. Photons are not made. They are allowed. They occur when conditions permit. They vanish when those conditions resolve. Darkness is simply the condition where allowance is unused. This way of thinking removes the need for finality. There is no last photon. There is no ultimate darkness. There are only shifting patterns of excitation and rest. Regions brighten, regions dim. Processes start, processes settle. Even black holes, often associated with absolute darkness, are not exempt. They emit radiation through quantum effects. They influence surrounding matter. They interact gravitationally. Darkness there is not emptiness, it is inaccessibility. And even the deepest darkness is not permanent. Given enough time, given enough fluctuation, given enough change, photons will appear again. The field allows it. This continuity is important. It prevents the discussion from collapsing into conclusions. Nothing here ends. It cycles. It ebbs and flows. Returning gently to the dark, then, is not stepping away from understanding. It is allowing understanding to rest without needing to resolve every question into a final statement. The universe does not require conclusions. It requires consistency. Photons demonstrate the consistency by behaving the same way, everywhere, every when. Darkness demonstrates it by remaining stable when nothing demands excitation. If there is a comfort in this, it comes from recognizing that absence of light is not absence of reality. It is simply a quieter configuration, and as the lights dim, as fewer photons reach your eyes, as the flow of information slows, the same field remains beneath everything, unchanged, waiting without urgency. There is nothing you need to hold on to here, nothing you need to remember actively. The ideas do not require attention to remain true. They exist whether they are thought about or not, much like photons exist whether they are detected or not, and much like darkness exists whether it is named or not. The universe does not insist on being observed constantly. It allows stillness. It allows low activity. It allows long stretches where nothing dramatic happens. Returning gently to the dark is simply aligning with that allowance, letting the messengers rest, letting the field remain, and letting the quiet continue without needing it to mean anything more than exactly what it is.